So basically, here's a summary of our slides. We have our introduction background work we did for this project, how we all contributed, the problem statement, control objectives, how we set up the simulation, our results, conclusion, references, and questions, if you wouldn't mind holding those till the end. So, like I've said, our project is over UAV landing on an aircraft carrier. Aircraft carriers are basically used as portable runways for many different aircrafts, including UAVs, and creating an autonomous UAV will help provide the Navy with time that they could be using towards other important things. So that's why we were decided to look into this.
So a lot of the literature review and the background work we did for this was to actually identify relevant information for solving our problem statement. And one of the ways we identified information was going through past assignments, determining the number of axes that our ship will be moving in, so we know how many transfer functions to have. And then once we determined how many free axes the ship moves in, determine how many axes the ship will actually move in. For example, this includes taking into account the fact that aircraft carriers have thrusters that largely negate their pitch and roll. And then we used assignment aids and filled in the gaps in combination and animation files. So this includes adding a C, adding object interactions, stuff like that.
So overall, our group kind of worked together. Once everyone had finished their certain parts that we each individually worked on, we came together to piece together every individual file that we kind of worked on. For Jacob, he was like the main source of creating a waypoint system, so how the UAV was able to find the aircraft carrier. Emma worked on the animation with me, making sure that she gets the C drawn in and really working on the F-16. And I worked on the combination of the air animation files for the UAV and the aircraft carrier and making sure that the Simulinks that we created for each individual one combined and worked together. Josh worked with David on researching ship dynamics. He created the parameters for the ship dynamics function and aided and created the waypoints with Jacob. And David assisted Josh with these ship dynamics and researching like the control technologies. So he really helped put together the Simulink for our ship dynamics. And so our problem statement modeling, our problem statement, as before said, we were simulating an autonomous landing on a moving ship. So our aircraft carrier was modeled after the Gerald R. Ford class of aircraft carriers, and our fighter jet was an F-16. As they are a little blocky, we weren't able to get like inputting a CAD model, as like our computers couldn't necessarily handle that. So we had to use different points and different planes to create our models. But our aircraft, they should be roughly to scale. I know they're not perfect, but they are very roughly to scale, so you can understand everything going on. The dynamics file for the aircraft carrier, as David said, it's simplified a little bit, so it negates all other rotations other than yaw. So we have a couple different like tests that we do, some with yaw and some without yaw. And that's due to like the thrusters that are in the aircraft carrier. And we did include wind for our presentation as well.
So when we were coding, we tried to identify what would be the hardest things to fix in the code to like make it run correctly, and then focus our time into that. And right at the beginning of the project, we knew that the most difficult challenge was going to be introducing updating data to the PID loops, because our assignment 8, all of our PID loops were set in stone when we ran the simulation. But this simulation actually has updating information in the heading control for the UAV. And then the second most difficult challenge would be introducing object interaction parameters between the deck and the UAV. So this includes stuff like making sure that the plane doesn't fly through the ship, making sure the plane doesn't fly through the sea. And this was a lot of defining the volume space of the aircraft carrier in the sea, and then continuously updating those volume spaces.
So this is what our Simulink really looks like. At the top here, we have the autopilot and the dynamic systems, as well as the animation to actually show us what's happening. We have the wind block. For this picture, we have it set to 0, but we can change it to increase or decrease the amount of wind. On the bottom left is where our ship dynamics come in. It's just the position north, east, and the angle that it's going at. And then the circled block is our autopilot inputs. So it gives us our heading, the altitude we need to get to, and everything else that we can to actually land the aircraft. And like I said before, the bottom left is just the ship dynamics kind of system running the ship.
So this is a video clip of our aircraft landing on the carrier with the ship having no yaw to it, so it's moving in a straight line. It's offset from the origin, so the aircraft will start at about 50 units, we could say feet or meters, but at 0, but the ship is, I believe, is 1,000 meters forward and 100 to the right. So the aircraft has to determine the waypoints and correct its course before landing. I did shorten the video a bit because it did run a little bit long. Here, you can play the clip. So you can see the y-axis changing. So the east. So it's coming in and it'll hit the first one of the waypoints, and then it will try to connect to the next one and continue down the chain of waypoints we've commanded it to hit. And it's hit the deck and landed. So that one wasn't too difficult for us to model, as the ship was going pretty straight. It wasn't a lot that the PID had to figure out to land. So that was that video. Now we have yaw. This was more challenging as the aircraft carrier is yawing, so it's moving both forward and sideways. So these points are swaying out and moving quite drastically as the ship makes maneuvers. So it's more of a challenge for the aircraft to perform this landing. Again, it's a shortened video, so you guys don't get to see it start at 0, but so it's coming in. See the aircraft correcting its course to try to have the same angle as the aircraft carrier and land straight on with the deck. Makes final corrections when it's landing, and it landed. So you can also, if you saw in both presentations, we have our slide gains. Well, we have graphs showing the performance of the PID loop. Right, and those were those.
Okay, so overall, we created an aircraft carrier UAV and made the dynamics files for both cases. We were able to determine the changes that we needed to make for the UAV to follow the different waypoints. We were also able to take all the information that we have learned throughout the semester and apply it to this project. We also learned a lot from this project, primarily how to think about the path of a UAV and how its velocity changes throughout the flight. Here are some of our resources that we used. Does anybody have any questions?
Right on time, guys. There's 19 seconds left. So yeah, I will open the floor for questions. Anybody, even from other teams, including judges, can ask questions. So go for it. Matt, Prashant, Krishna, Anushna.
So this is Matt Romero. I have a couple questions. I'll ask the first one, and then I'll wait for the second one until see if anybody else has any other ones. But in doing this, what were some of the things that you learned in troubleshooting this project? You know, how many times did you actually go through it before you got to success?
This is David. I can answer a little bit about that. One of the control objectives we talked about was defining the object volumes and the object interactions. We did a lot of troubleshooting with that. That was definitely one of the things where we ran the most trials trying to figure out.
Yeah, we also, with the Waypoint system, there was a lot of like updates and revisions to it, where originally we had the waypoints where it wasn't actually yawing with the ship, so we would get weird approach angles and stuff like that. So we had to revise that quite a bit till it actually worked where the waypoints were in line with the deck of the ship. So that was definitely a challenge and took a lot of work to get that.
A question about the waypoints and control, because giving set of waypoints is at the path planning layer, and then applying a PID is at the control layer, correct? So how was the interaction achieved? For example, you give a waypoint and then it's trying to reach that. So you the second so it kind of tries to servo to the first waypoint, and then from there it goes to the second waypoint. How is it done, that interaction?
So we did it as a simplification for this, where we were attempting to do it where if it hit within a certain region around the waypoint, we said it was a successful hit, and then would move on to the next one. I ran into some problems with that.
Sure.
So
Sure. That makes sense. Yeah.
We made a big assumption that our ship will always move forward. So within our loop, it's just as long as the ship does not turn around and go into a negative direction, it's just the first waypoint is the furthest one back, and it's just moving onwards. So it's like the closer to the waypoint and further away, it'll go to the next, and then the next, and then the next. So that's kind of how we accomplished that. Kind of a little bit, it made it easier on us rather than making the sphere of successful hitting, well, like a successful approach, I guess would be the best word for it.
Okay, great, thank you.
Yeah.
Hello.
Hi.
Yeah. So, could you go back to your Simulink diagram slide?
Yes.
Yeah. I was just wondering, what is that quantity, that 53.89 at the bottom left corner?
That's a clock.
Oh, okay, okay, okay. I see, I see. And I had another question. So, I just heard your answer about describing how you had the sequential waypoints. Is there a specific way you choose the waypoints?
That was more of a trial and error to see what the PID could successfully do to land on the deck.
Okay,
So
okay.
we thought of like, all right, what's a pretty good glide slope for an aircraft to land on on a deck, and then we just kind of played with that to see what the PID would do and like how it could actually successfully do it without making really sharp turns or being too high and then having to nosedive to the deck. So we just kind of played with those numbers till we got a good animation.
Okay, okay.
We had pretty smooth values.
Okay, okay. Thank you.
Yep.
Yeah, we ran into an issue where the last waypoint, the ship would be, or the aircraft would be above the aircraft carrier deck, but the wing would kind of dip below the aircraft carrier deck. So that was kind of like what David was talking about, working on object interactions, because it hit the last waypoint, but like the aircraft crashed. So that was something we really had to iron out towards the end.
Matt, did you have more questions?
I had one more. After going through all this and knowing what you learned, how would you change it if you had to do something different to start a new project? What would you start? What would you do different in doing this? Where would you start?
So for me personally, it would be probably ironing out or actually successfully accomplishing a waypoint system where the aircraft enters the zone, and if it does, then it progresses to another one rather than more of a linear progression where as long as you pass this length, then go to the next waypoint sort of thing. Because then we could have implemented a go around system or a lot of other interesting aspects that I think were a little bit lacking with this one.
Yeah, I'd have to agree with Jacob. I think something that I would really like to do or just kind of build off of is maybe taking off from an aircraft carrier or saying it missed the hook, like going like hitting the thrusters full go, and if it missed like the point on the aircraft carrier deck, hitting the thrusters full go and then looping back around, see if we could get that. But we just hit a lot of time constraints towards the end of the semester.
Sure, of course. Thank you.
Yeah, thank you. Prashant, do you have a question or should we move on to?
Do we have time for questions?
I think we are, yeah, I think we are done 5-minute mark. So yeah, let's team two.
Let's move forward.
Yeah, let's team two share their screens. Yeah, thank you, team one. Good.
Thank you, everyone.
Job.
Thank you.
Thank you. Thank you.
Yeah, team two, please share your screen and.
Yep, can everyone see that?
Yep, so your time starts now.
Great. Good morning, everyone. We are Team 2, and we also did modeling and simulation of landing a UAV on a moving ship. So some of the topics we're going to cover today, we have a lot of stuff to cover in a lot of detail, so I do ask that you hold all questions until the end. And to kick things off, we're going to start with team introductions. David, I'll hand it over to you.
Good morning, everyone. My name is David Holtzclaw. I worked on the UAV dynamics.
Hello, I'm Ryan West. I also worked on the UAV dynamics.
Good morning, everyone. I'm Tony Fasciola. I worked on the animations and the slide design.
Hello, I'm Grace Fisher. I worked on the ship dynamics.
And I'm Lindsay Alverson, and I helped with the animation.
So to go over what we identified as our problem overview and what we proposed as our original solution, we're really going to focus on this right column for our case. So we wanted modeling, simulation, and control of a fixed wing UAV. We also wanted modeling and simulation of a moving ship at a variable speed. And then really this was the big focus, was we wanted realistic landings of the UAV on the ship. We wanted the UAV to track the movement of the ship. We wanted support for missed approaches. And we also wanted our animation to dynamically update to zoom in on the details as the ship began to land. Here's some of the literature we covered. A lot of this was used in our dynamics models. And now I'll hand it over to Lindsay to start detailing the animation.
So at the beginning of this class, we learned how to import STL CAD files into MATLAB. So we decided from the start that we were going to model our UAV and aircraft carrier in Autodesk Inventor and then import it in for our animation. So Tony took the reins on deciding that we would model the MQ-25, an up-and-coming aircraft carrier companion, for aerial refueling as our UAV, just because it's very symmetric and it's something very relevant to the Navy currently. And then we modeled our aircraft carrier just after a basic aircraft carrier design. And then I worked on importing his STL files into MATLAB and ensuring that every time the animation ran, it would be at the 0, location and that all the rotation matrices worked correctly with how he modeled each of the simulations. And then Tony and I also worked on making the visualization better by having the axes of the simulation automatically update as the UAV was flying, and we also added in planes of water and a sky, but due to the interest of runtime and the functionality of the dynamics, we needed to comment those aspects of the animation out so that the dynamics would run better. And I will hand it over to Ryan and David to detail those dynamics.
So over the course of this class, we created a working autopilot using several PID loops and control states. What you're seeing here is a control state diagram that we created for this project. The first 3 states that you see on the right, the descend, altitude, hold, and climb, come from this original autopilot. And the other 3 on the left, landing, on carrier, and missed approach, are the new states that we designed for this project that will be explained in further detail on the next slides. So for the majority of the simulation, we used the original descend, altitude, hold, and climb states, but we modified this using a path following system, a dynamic waypoint system that used the position and heading of the UAV relative to the carrier to determine the position of the waypoint that the UAV would head to. As you can see on the diagram, with the blue triangle, if its heading is opposite that carrier, it would head to a point much farther back on the carrier to give itself time to turn around and align itself. And then with the other three, with the green through the red, it slowly moves that point farther forward behind the carrier so that it can gradually adjust itself to align itself with the carrier. And once it aligns itself with the carrier within a certain tolerance, it begins its final approach, and where it slows its height and lowers its speed. And then it goes into the final approach.
So as Ryan said, once it gets within those tolerances, it will then conduct its final approach landing. If it doesn't get within those tolerances, by this point, it'll go into its missed approach, which will be discussed later. On the final approach, the plane will pitch up to decrease speed and height, and so it can maintain a 3-point attitude on the landing. Once it does go and touch down on the deck, the UAV will decelerate under friction until its relative speed is 0 on top of the moving carrier.
As we mentioned before, we added a missed approach feature so that if the UAV falls outside of certain tolerances in its landing approach, it will hit the maximum throttle and pitch up to climb to a certain altitude and continue over the edge of the carrier before safely turning around and attempting another landing. And now I'll hand it off to Grace to explain our ship dynamics.
For the ship dynamics, instead of working with 6 degrees of freedom, the motion was simplified down to 4 degrees of freedom: surge, sway, pitch, and yaw. The ship is given a velocity and heading angle, and there is also a wave force to induce roll and pitch motion. However, due to the need to reduce simulation runtime, the wave force is a constant and the rocking is even. The parameters were adapted from a cargo ship to a carrier ship for this dynamics. On the bottom, you can see the equations of motions that I used, and on the left you can see the motion of the ship relative to the stationary UAV sitting at the origin. And now onto the simulation setup.
To briefly go over our simulation setup, really the way that this is structured is we are able to issue some commands for the ship speed and for the ship heading angle. Then the ship dynamics computes, as Grace just discussed, and those states go directly into our UAV autopilot, where some of those commands are used, as David and Ryan discussed. Really, some of the big details to note here is there was a couple changes you can make for performance improvements, including lowering the tolerance, swapping over to a stiff ODE solver, and then also disabling crossing control. Now I'll hand it back to David and Ryan to discuss our simulation.
So the first thing you'll see in our simulation video is a missed approach. So the UAV went through the landing control phase, but it's not within those predefined tolerances. And so you'll see right here, it pitches up, zooms away, climbing to that predetermined missed approach altitude that Ryan mentioned earlier. Once it reaches this climb altitude, the plane will check to make sure that it's away from the carrier. And then once it does, it'll engage the dynamic waypoint system that Ryan also discussed earlier, going to a point that is, at this point, well behind the carrier. So as you can see now, the plane is heading towards that point.
As David explained, the UAV will continue heading towards this point very far behind the carrier. You can also see that the axes of the simulation dynamically adjust to include both the carrier and the UAV for better viewing purposes. The UAV is just about at the point behind the carrier where it will begin turning around and aligning itself with the carrier. Also of note is that this test case was just sort of chosen at random. There was no specific reason we chose the carrier at about a 45-degree heading angle. The way we have this designed is that the carrier can be placed at any location and the UAV can start anywhere and it will successfully land. Here we see now that the UAV has aligned itself with the carrier, and shortly it will begin lowering its speed and height to head in towards its final approach that you'll see here shortly.
So the UAV is about to enter its final approach. You'll see the UAV drop in height, and then it'll enter that final landing control stage where it'll pitch up right about here to get that soft glide in for the touchdown on the deck. And then once the UAV does touch down onto the deck, it'll slow down to a stop. This image shows our state plots for our landing. You can see in the height command at the very beginning, the missed approach, and then our UAV landed around the 122 second mark.
To wrap up for today, we just want to go over quickly some of our conclusions. In terms of outputs, as you just saw, we have a working model of a fixed-wing UAV landing on a moving ship with unique animations supplied along with a working carrier dynamics model. We also met multiple of our stretch goals that we laid out at the start of the project, including support for things like deck friction, missed approaches, and even some basic simulation optimization. Some of the lessons we really took away from this was that the optimization part of the project really begins at the architecture level when you're starting out. There is some work you can do in Simulink, but a lot of work needs to be done with how you actually define and manage your S functions to make sure that your refresh rate can stay quick. And then additionally, we've realized that modeling is a multifaceted optimization problem. And what we're getting at there is really that you need to come to an agreement at the start of your project on what level of fidelity you're going to be satisfied with your model, and also how much time that will take to complete that model. And then if we had some more time to continue working on this, we have a couple of further improvements, including support for a complete flight plan, including both takeoff and landing. And then we'd also like support for multiple aircraft sequencing onto and off of the carrier. So with that, we'd like to thank everybody for your attention today and ask if anyone has any questions.
That's perfect. My alarm just went off, Great timing. You guys practiced pretty well. Yeah, pretty cool simulation, very detailed. So yeah, I'll open the floor for questions from judges.
So I have a quick question. It's Matt Romero. When you guys were looking at your landing of the UAV on the aircraft carrier, did you only have one point that was a successful landing point on the carrier, or did you have multiple set up? So aircraft, and the reason why I asked that is because aircraft carriers typically have like 3 or 4 catch cables for an aircraft to land successfully. So it gives them a few options, so that way they don't have to pull up or pull away, unnecessarily. So just curious if you had more than one on your carrier.
Hey, good morning, Matt. This is David. The way we defined the landing position was within a certain tolerance. So if the plane was over the deck and within like a certain height for a particular span of the deck, then it would complete the landing. So as far as like the multiple cables, I mean, that way, smaller plane could get along further on the deck and still complete the landing.
Okay, thank you.
I have a quick question, Prashant. So if you had to increase the fidelity of this problem, what would you do? Do you have any ideas of what would increase it?
Yeah, thank you, Dr. Curray. So really one of the big things that we'd like to include is, like Matt and David were just discussing, is really having that carrier catch cable incorporated. For this one, in this case, we really just have a deck friction model to slow down the aircraft. But yeah, ideally with the way that modern carriers work nowadays, we'd like to have a cable catch for sure. And then as well, we'd also, as we mentioned on the last slide, we'd like to have multiple aircraft flying in and out and sequencing into the carrier in order to really provide a true operational view to show a simulation of the density of the operations.
Thanks.
Yeah.
What about, so go ahead, Krishna.
Yeah, maybe that was my follow-up. You were about to ask, or I was thinking, how about wind disturbances? That could be one way of enhancing or making it more realistic. Correct. So have you?
Yeah, that was actually my question. Plus enhanced aerodynamics for your UAV.
Yeah, so we actually do have the wind implemented. Let me switch back to the simulation slide. In this case, we do have it turned to 0 for the sake of the simulation, but that could easily be altered in the parameters of the file to support wind.
When you say, then do you have the equations that like represent the Okay, so it probably it's just like a wind force, correct? So external forces, it will be part of the external forces.
Yeah, maybe, and David and Ryan can probably touch a little bit more on this, but we do have the equations. Those were reused from our earlier autopilot assignment from this year, and we can get those to you after today.
Sure.
So yeah, I think wind is a part of that's how you compute your airspeed. So aircraft speed and wind speed gives you the airspeed using the wind triangle. So yes, I think from that perspective, I think the model was pretty rigorous in terms of including wind in the models. But I think still Dr. Khare's question was if you have to improve, if you have to make it more realistic, what assumptions we have made which could have been, like from fidelity perspective, did we leave anything out? That was his question.
Was precisely my question. Probably most people in this class will know how heavily I lean on assumptions.
Yeah, I mean, there's also there's a lot of work that could be done to increase fidelity, and stuff just needed to be left out as a result of the time constraints. But one of them really is we'd like to be able to get a more accurate view on the actual aircraft itself. Some of the parameters that it runs off of are really just generic and are reused from our autopilot assignment earlier this year. Obviously, those are not entirely correct for that MQ-25 that we used in this assignment.
Bouncing off of what Tony mentioned, I think parameters, the more realistic landing, not just a simple friction model, and then also what Grace mentioned earlier, where we had a more robust ship dynamics model ready, but due for the sake of the simulation and time restraints, we had to restrict that a little bit. So adding fidelity in those three places would enhance our simulation.
Thanks, David, Tony. Good job.
Thank you, Dr. Gray.
Okay, I think the 5 minutes are over. So team 3, please. Thank you, guys. Thank you, team 2. Good job.
Thanks, everyone.
Thank you.
Thank you.
Thank you.
So team 3, when you are up. So there's a lot of competition going on between landing stuff.
All right. Do you want us to start now?
Yeah. Start time. Your time starts now. Go for it.
Okay. So we are also landing a UAV on a moving aircraft carrier like the past two groups. We are team 3. I'm Daniel. You can see Kellen, Alexi, and Jackson with their cameras on as well. So our contents, this is a brief overview of the contents of the paper. Not going to spend too much time here, but we go through our research and background work. We step into the problem statement, areas of application in real life, and then we also talk through our formulation of our modeling and our simulation setup. So with the increase in use of UAVs in various branches of the military, the autonomous landing of a full-sized UAV on a moving ship is a large part of the near future of aerospace. So for this project, we chose an F-22 model. It'll begin at an initial altitude behind the ship, and it's going to have an initial velocity as well. And it'll land on this moving ship, lowering its velocity. And we're also going to set up a course angle different for the plane and the ship to cause some course correction in there.
Hi everyone, this is Alexi speaking. So for our first objective for solving this problem, we wanted to model the ship dynamics and plane dynamics in the same Simulink and as well use a single animation file. The ship's dynamics outputs and locations would then become part of the inputs that go into the commands for how the aircraft would react. Our second objective was to have a single animation file that can take in the 12 inputs from the boat and 12 inputs from the aircraft and use them to animate them both in a single file. And finally, we also wanted to have a what we call a high-level autopilot. This reads in the different dynamics and finds the different locations between the ship and the aircraft, and this will automatically adjust the course and pitch commands to then bring them together. We used a tail chase methodology with a geometric approach to have a nice and smooth landing.
So for our research papers used, we reference the two works below. This is a problem that has been solved before, but we used two different papers. One, the mathematical ship modeling for control and applications, and leader-based multi-agent coordination, controllability, and optimal control. We kind of put those two together and formed our simulation. For our contributions to the community, we showed that what a geographically distributed UAV with autopilot capability of converging onto a moving target. We added variable wind gusts to the model for a realistic landing situation. We are able to adjust the UAV for course landing on a ship with different course angles, and we displayed that the UAV's ability to adjust flight states to safely land on the deck of a aircraft carrier. Areas of application, this kind of feeds into search and rescue, UAV communication relay, and unmanned aerial vehicle surveillance, intelligence, and reconnaissance.
As far as background work and equations, first we set up our dynamics, animation, and parameter files that we developed over the semester for our UAV and autopilot. We made sure that the UAV could perform the tasks when inputs were given. As shown below, the 12 governing equations set up the model for our flight, and again, they were developed over the past assignments from the semester. These equations output the variables that govern the plane. They're the PN dot, PE dot, PD dot, U dot, V dot, W dot, Phi dot, Theta dot, Psi dot, P dot, Q dot, and R dot. We then made a boat dynamics file using the resources provided that Kellen just talked about. From this, we simplified it down to 2 degrees of freedom just for simplicity purposes. So we neglected the pitch and heave, and you can see our equation of motion listed on the slide. We then had our transformation J matrices, which are also listed on the slide. And from this, we output our U dot, V dot, P dot, R dot, as well as the U, V, W, P, Q, and R for the boat. Finally, we used the states of the ship, the airspeed, course command, and the height of the UAV are found so that it may land on the aircraft carrier. The following MATLAB code is what we called our high-level autopilot, and this code basically brings the states of both the ship and the UAV, then sets a waypoint behind the ship. Once it reaches the waypoint, by deciding course commands through our high-level autopilot, the UAV then goes, once it hits the waypoint, it then goes to the ship and lands on the deck of the boat.
All right, so for the modeling of our simulation, we took out the role in our ship dynamics to just focus on the UAV adjusting the course, so we didn't model our waves, we just modeled a different course angle. Our UAV initially navigates to a preset waypoint behind the ship, and then it will lower its velocity and its pitch to make a geometric tail chase maneuver onto the rear of the ship. And then once it came within this specific radius, we modeled the ship deck as like a set landing height. And this allowed the UAV to, once it hit that deck zone, it would mimic rolling across that deck rather than continuing to go down through the ship. So for our control objectives, we wanted to set the course of the aircraft carrier onto the current course that would be held throughout the simulation. So in one of our runs, we did a straight course that aligned with the initial course of the plane, and then another one we set it at a different angle so that the plane would have to correct. We have a high-level autopilot file which allows this UAV to read the updated boat positions as it moves, and it feeds that into the autopilot commands. And then we landed on the boat using these adjustments and our previous homework's autopilot file. And the following Simulink file shows a more detailed version of the way that we read in these values. So we take our values from our boat dynamics file, put them into a Simulink block rather, and then we put it into a demuxer. It comes out into the dynamics of the plane, and then all of these states come out together back into the autopilot for the next stage after the initial values. And then, so the high-level autopilot takes in the dynamics of the boats and the UAV, as I said in the previous slide. It then uses math that we created in our equations to determine the distance between the boat and the UAV. And then this is how we auto-update our command values, being the velocity, the requested height, and also the requested course. So it first travels to a waypoint that we set about 100 meters behind the boat, and then it'll make this turn so that it has time to level out with the ship, and then begin its descent and deceleration in a stepping manner until it hits the rear of the ship.
So Daniel kind of just stated what it steps through to get to our final output. So to model that in Simulink, we kind of took that exact stage or that exact process, and we found the boat dynamics that then output into our high-level autopilot that then outputted states into our regular autopilot, and then it kept generating through until we got a correct simulation. Here are our results. This is a UAV landing on a carrier at 30-degree course angle. There will be some stutter due to the size of our CAD files. Just right here at the end, you can see the boat stuttering just a tad. This now on to the next one. This is our UAV landing on the carrier with a 0-degree course angle. Again, a little stutter due to the sheer size of our CAD files.
Here we have a snip of our plots from landing at different initial course angles. As you can see, our height, course, and theta graphs track well. We do have some steady state error, and some of the graphs do look a little off just because we had trouble getting those to track the proper variables. And then here is our plots for landing at the same initial course angle. Again, you can see that our height, course, and theta do track well with some steady state error. And again, some plots are just slightly off due to having trouble tracking those variables properly. And then just some brief discussion about our results. As you can see in the videos, the UAV correctly tracks and lands on the boat in both the angled and straightforward attempts. We do have wind modeled into our simulation to give our UAV something to move against and give a more realistic feel to the model. And although we did have good results, some of the limitations that we had were due to the boat not being on an autopilot, so we had to manually set the course for the ship and give it a thrust forward. Another limitation that we had in our model is the simulation does not incorporate waves into our mix. This allows for our boat to be very stable in its process, and the UAV does not have to adjust its course or roll to correctly land on the boat. And again, as Kellen stated, the last limitation in our simulation was due to the size of our CAD files, and it tends to stutter a little bit in the videos.
Guys, your time is over, so can you wrap up in a couple of seconds?
Yeah, I can briefly just say this. We briefly wanted to add those dynamics and add the autopilot to it. And then in conclusion, we believe that it's a lot easier for it to land with the same initial course angle. We noticed a little bit of wing dipping like the first group talked about on a different initial course angle. We found that a rear waypoint is necessary because the plane can't make the banking turn. It needs to go to somewhere behind it first. And do you guys have any questions?
Yeah, thank you, Team 3. So questions for the team?
The speed of the aircraft, while just before landing, in general, did you match with, the real speeds that are involved in aircraft?
We tended to model it more based on our past assignment speed of the aircraft. We set the boat to a constant speed, and then as we brought the aircraft in, we were more concerned about it stepping down. We started it at a considerable higher velocity than the ship, and then stepped it down as it got closer to allow it to, almost when it hit the boat, simulate that hitting the chord and slowing it down fairly quickly once it hits that deck area.
Okay. I guess my question was,
that?
did you match it with speeds of real fighter aircraft? Did you do any verification like that, the speeds that you're using?
No, we didn't match it to a normal fighter aircraft. We were more focusing on the actual landing due to time constraints.
Okay, yeah.
Other questions? Krishna, Matt, Prashant.
Can you go back to your plot files, like where you show the graph, either for the same course angle or the different? So I just had a question, like in your roll, pitch, and yaw rate, so basically PQR, what is that blue line? Could you just explain the legends on the graph?
Yes, so this was actually, we don't believe that that's actually our P. We think that we tracked a wrong variable, but we ran out of time in doing this plotting because the plotting was the very last stage after we got it to land properly. So we think that it's tracking some sort of other variable, or it could be due to the fact that when we implemented the value of the deck being a deck, the plane is like supposed to hard stop at that altitude. So we think that it could be a little bit of unsteadiness that comes from it almost like having that hard stop on that deck.
Okay.
Also, you don't know if they are degrees, radians, because 200 radians per second or degrees per second. It's a lot of rolling going on there.
Yeah.
Yeah.
Okay. Any other questions for team 3?
Yeah, I don't have any others. I was actually going to ask the same as the last question, so I'm good to go. Thank you.
Thank you. Okay. Thank you, team 3. Good job. We'll let team 4 share the screen.
Can you see that? Okay.
Yep.
Okay. So this is our project on Orbital Rendezvous, the simulation of Orbital Rendezvous.
So just to give a brief introduction, we're considering two bodies, one being a spacecraft, which is the chaser, and one being the satellite, which is the target, and they're orbiting a large body of mass, which is, in this case, the Earth. And the orbital rendezvous is just a set of maneuvers during which the spacecraft arrives at the same orbit as the satellite, which is followed approaching a very close distance from the satellite. And the meeting of these two involve very complex maneuvers that are intricate, balancing of gravitational, Coriolis, and centrifugal forces that are acting on the spacecraft. And this has caused problems in the past with the Gemini missions because they're so intricate and complex. And so in our work, we show the necessary impulse for the spacecraft to reach the same orbit as the satellite, and then successfully dock with the satellite and get very close distance. And we want to plot the trajectory of each body, as long with calculating the impulse. And we want to demonstrate the complexity of the dynamics involved in this problem and the importance of careful consideration of the value of impulse performed by the spacecraft.
So we created a model showing a target satellite in a constant circular orbit and a chaser spacecraft adjusting its own orbit and position in the orbit to rendezvous with the satellite. The model considers the initial altitudes of the satellite and spacecraft and calculates their initial velocities, the chaser's impulse, and position of rendezvous.
So the related work, we basically use a lot of mechanics from a paper published by Bradley Carroll entitled The Delicate Dance of Orbital Rendezvous, where he basically overviews the relationship between the position of the chaser versus the target in orbit, in the target's frame around its circular orbit. This is a really complicated topic that we also had to take some data from Buzz Aldrin's paper, which is line of sight targeting for orbital rendezvous. In the bottom left there, you could see a plot of the position relative to the target as the two bodies are orbiting. And in the right, you could see some of the models that are used in the paper that we used to model the simulation. In the left, or in the middle plot, you have the full Earth trajectories of both target and chaser, and then in the right it's just the target frame.
So as you heard, the model is representing a target, chaser, and Earth. The target is in a circular orbit, and so is the chaser. The chaser follows a specified impulse node and then will move to the target and perform a rendezvous. Under these modeling conditions, we had some assumptions we made where both trajectories are coplanar, so we're only dealing with 2 planes there. The chaser and target are considered massless points with no rotation, so we have no inertia, no rotation accounted for. Thrust maneuvers are simplified into an instantaneous impulse, so normally with an impulse, you have it specified over a period of time, or in this case, it's just instant. And the nonlinear terms of motion for the equations of motion we used are disregarded. Liam, if you wanted to handle the reference frame.
And then in the bottom right, you could see the reference frame that we're using. What you'll be seeing in the animation is going to be in the star frame or the inertial frame, which is basically the macroscopic view of the entire thing. But most of the actual equations of motions are dealing with the non-inertial frame, which if you could see the smaller the y and x axes at the target is what that frame is. And it's the position of the chaser is relative to that.
So just explain some of the dynamics involved in this problem. So equation 1 is just talking about the position of the satellite, which is orbiting at a constant angular velocity, which is defined by equation 2. And it's from the non-inertial frame, which is the center being the Earth. But the position of the target is actually modeled, or I mean the chaser, my bad. The position of the chaser is modeled with the non-inertial frame, which is actually the center being the target. And so the complexity of these equations are a little bit more than the target. So, and all of this is respect with time, because I'm talking about equations 3 through 6, because the position of the target is constantly changing with respect to time because it has a constant angular velocity. So, and I'll hand it off to Liam to explain equations 7 through 8.
7 and 8 are a derivation of the what's the name of that body of equations, Sam? The Closey-Wiltshire. The 3 through 6 are Closey-Wiltshire. 2 is Kepler, third law, and then 7 and 8 are derivations of those that seek to find the initial y and x velocities that you're going to need to rendezvous at a certain time of flight, which is specified.
The inputs to our models are the altitude of the target, the initial altitude of the chaser, and the time from the impulse to rendezvous. The combined dynamics block then takes these inputs and calculates the initial velocities of the target and chaser to start the simulation in circular orbits. It then calculates the required impulse to rendezvous with the target. The chaser and target positions are their orbiting paths and then drawn within the animation block. An interesting feature to note is because of how different this problem is from our previous assignments, we did not use a PID loop. This is because orbital mechanics require discrete and very precise impulses to change orbits. And due to these reasons, the PID loop was unnecessary to include in our model.
So our next slide is going to include a video of our one of our simulations. And so I wanted to go through the parameters first. So we set the altitude for the target to 400 meters, and the initial chaser altitude is set to 1,000 meters. And the time of flight for the target to reach the chaser is 1350 seconds, and we set the mass of the Earth to be 5.972 times 10 to the 24th kilograms.
Here's a video of the simulation. I'm going to walk it through, I think. So it starts off, chaser and target are both in circular orbits. The chaser is in a higher orbit at 1,000 kilometers. Once it hits the impulse point, it's going to perform an impulse right there. You can see this is an impulse vector in the direction that it was calculated to meet this rendezvous point, which is the blue dot. And then you could see the following will be a trajectory, the corrected trajectory to arrive at the rendezvous point. After they hit the rendezvous point, there is going to be It is not shown, but there's going to be a second circularization impulse here that will correct the chaser's velocity, basically just removing any difference between the chaser and actually be in effectively be in zero relative docked orbit.
So as for our results, you can see that from the video we have 2 successful impulses and a successful maneuver point specified where the chaser will meet up with the successful target rendezvous. We also have predictive mapping of the target and the chaser pass after each impulse. So as you saw, we had that red line and then the purple line once they had simulated a docking after rendezvous. We do have some limitations here where we have the model is complator that was made in our assumptions. The chaser auto docks within the specified distance to the target, so the dynamics for the chaser and target become the same equations of motion to describe what's happening. The impulse is instantaneous, so we don't have any time period within the impulses for both of them, one for the chaser to the target and one to correct, as Liam stated. Point models, so we're now representing inertia, rotation, some of the complexities that come with an actual model, even though we had a 3D visual representation there. The model is simplified for linear simplifications, and the complexity and difficulty of PID was not included because of the orbital mechanics in the model were taken into account.
Here's some conclusions. Basically, to improve, we use z-axis, going a bit over time here, but here the rest of these conclusions you could read. I will provide the presentation. Here are our references. We use the, like previously stated, Bradley Carroll's Delicate Dance Orbital Rendezvous and a little bit of Buzz Aldrin's line of sight guiding techniques. And that's it. Any questions?
Thank you, Team 4. Good stuff. Yeah, I'll open the floor for questions, judges.
Good job. This is Prashant. I have a quick question, maybe not related to what you've done, but generally the way impulses are given is called delta V, and it's given by using thrusters, which eject gases. Did you look into how these impulses are actually given, and do you have any thoughts of implementing it in your simulations?
Well, the model we used from Bradley Carroll's paper calculates the impulse as some amount of velocity, like you stated, basically a delta V. We were unable to go more in depth into the actual impulse without needing a lot more time, just due to the complexity of the simulation. But we did take that into account. So yeah, the impulse is calculated with in meters per second relative to both orbit trajectories.
Mm-hmm. Good. The reason why I asked this question is because this is sort of related to gas dynamics. Actually, some of the things that you learned there can be applied right here for delta Vs.
In a future rendition of this, I would love to go deeper into that. I think we had a lot of fun with this project, and we may continue to work on it further.
Yeah, I have one question. This is Matt Romero. So did you guys do a lot of different runs with varied altitudes, and what were your results when doing that?
So in this specific run that we showed, we kind of had to jack up the orbital radius for the chaser a lot, because with the animation file, most of it is to scale. So if you have them only like 100 kilometers apart, it's kind of difficult to tell the difference. So we had to jack it up a lot, but the other simulations with different variables stay pretty accurate. The only problem is when you increase the time of flight a lot, it gets a bit buggy with these equations of motions, and sometimes if you take it too far, it'll just want to shoot the chaser off into some random extremely high orbit that'll just pierce through the Earth to try to meet the rendezvous point. But generally, most inputs, you can see a pretty reasonable result.
Okay, thank you.
So right now you used a 2D plane model, correct?
Yes, right.
How fair is that assumption and then extension to a 3D case?
I think this assumption is a pretty good model of what we're doing, especially because often when these kinds of rockets are launched, they are launched coplanar with whatever target they need to dock to. So it makes a lot of sense to use this assumption. But for a 3D case, basically the changes we'd probably need to make is we'd first need to make another impulse that would change. If they're at two different planes, they would need to perform an impulse at one of the intersections to basically first make them coplanar, and then they would conduct a separate rendezvous impulse like you saw. So this simulation would be like the second step of that process if we were to expand it into a three-dimensional.
Okay, thank you.
Any other questions? Okay, if not, good job. It was impressive stuff, Team 4. Thank you very much.
Thank you.
We'll ask Team 5 to share their screens. Okay, your time starts now.
Okay, hello everyone. My name is Josh Lupi, and we're going to be moving back to the autonomous UAV landing on a moving ship. So my team members are myself, Josiah Herring, Patrick Bentley, and Bradley O'Connor. So kind of start off, we're going to do a little brief background on the project, and then we're going to dive deep into the methodology behind some of our main dynamics. And then we have two results. We have two case studies that we did, one starting with the UAV from the right and one with the UAV from the left of the aircraft carrier. And we're going to talk a little bit about kind of how the results come together in the end.
Okay, so for this project, we're looking to autonomously navigate a UAV through a series of waypoints that are continuously updating behind a moving aircraft carrier until the two converge. And the UAV will target the aircraft carrier by an autopilot control that has a special navigation system implemented. So we will go about doing this by having the UAV and the aircraft carrier start at two different defined locations, and then the UAV is going to have to navigate to a waypoint behind the aircraft carrier and properly align itself so that it can land from behind. It will have to reach the proper deck height so that it can land without any collisions on the aircraft carrier, and it will have to accurately adjust its speed so that it can land and come to a stop on the aircraft carrier. We're assuming here that the external factors have a nominal effect on the aircraft carrier's movement, so things like waves and wind don't prevent or get in the way of the aircraft carrier moving straight and remaining level. And we're also assuming that once the UAV does land on the aircraft carrier, it will become fully attached.
So to model the dynamics of the aircraft carrier, we use the equations of motion you see on the right. We used a simplified version of this that included just 3 degrees of freedom, the surge, the sway, and the yaw. And we were able to use only 3 degrees of freedom because we assumed the aircraft carrier would be traveling in a straight line. And then to model the dynamics of the UAV, we use the UAV Autopilot that we developed in class. This Autopilot allows you to input an airspeed, altitude, and course heading. And then using PID controllers, it will continually correct the throttle, rudder, and aileron values to approach your inputs. This Autopilot also accounts for external factors like wind. And then this Autopilot then enabled us to implement a guidance system, which Josh will now elaborate on.
The guidance system is basically the block that goes before the autopilot. So the guidance system does two things. It creates waypoints, and then it also creates the inputs for the autopilot. So the velocity, the height, and then the course heading, so that the UAV can then go to those waypoints it creates. So what kind of helped us a lot to simplify this problem was, since the altitude is already an input into the autopilot, you can kind of negate the z-axis. So we created a 2D problem, as you can see from the coordinate system on the right. So basically you just have a north and the east axis. So it's a 2D plane if you look at it from the top. And the main thing to understand from the guidance system is what the course heading actually is. So course heading is your chi angle. And basically it doesn't matter where you're at in this coordinate plane, as long as you are facing the plus north direction, you are going to be having a course heading of 0 degrees. So if you turn directly to face the positive east direction, you're going to have a 90-degree course heading. And that's really important to understand. And then basically what you're going to find is your delta chi is your change in course heading between these course heading angles. So for an example case, you would have a UAV, let's say flying at, this looks like around 45-degree course heading, and your waypoint is this green dot over here, and you need to figure out how to get to that green waypoint. So to do that, basically you're going to set up 2 vectors. You're going to have a velocity vector from the UAV and a position vector from the UAV to the waypoint. So the velocity vector, you basically just use the velocity that the UAV is flying at to get the magnitude of it, and then you find the x and y coordinates of the tip of that vector, and you can create that velocity vector just by simplifying the x and y coordinates by subtracting them from each other. And then the same way with the position vector, you can just take the 2 points that you already know that you have, and you subtract them from each other to get the position vector. So now that you have those 2 vectors from the UAV, you can just find the angle in between, which is going to be the delta chi angle that you need from using the dot product between them. So once you get that delta chi that is not your course heading, you basically need to take that delta chi and either subtract it or add it to your course heading. So as you can see here, this is your course heading. To get to this, you need to subtract the chi, the delta chi to get to the course waypoint. But if it was over here, you need to add it. So you need to add in some case studies there to properly allocate for your delta chi. So what our waypoint system does is it creates 3 given waypoints. Basically, you have 3 set waypoints, and it continuously updates as the ship moves forward. So when the ship moves forward, you have your first waypoint, which is substantially far away from the ship, and then you have your second one closer, and then your third one is on the ship. This allows for the UAV to get in a position behind the aircraft carrier and then allow itself to straighten out so it smoothly lands onto the aircraft carrier. And then moving forward to our first case study.
So we're going to go ahead and look at the first case that what she did was starting the UAV from the right of the aircraft carrier, and we'll go ahead and play it. And you can see it right away. It's correcting its course to head to that first waypoint, and its altitude also corrects, and it hit that first waypoint, and now it's correcting to the second waypoint. And now it looks like it hit that second waypoint, and it's starting to level out to land on the aircraft carrier. Hit that third. And we can take a look, if you take a look at the position east graph, you can kind of see the position correct at about probably 16 seconds after it hits that first waypoint. And you can also see how it behaves around the waypoints if you look at the altitude, because its altitude's always going down, and then it hits that first waypoint and it starts to level out. And you can also see, if you look at the course angle, it, as the position vector and the velocity vector become more and more, I guess, parallel, the course heading direction starts to level out. And we can go on to our next case, which is just starting from the left of the aircraft carrier. And you can see it turns right to match the position vector of the waypoint 1. Then hits the waypoint 1 again, as it did last case, and it corrects to the second waypoint. And it just glides in nice and smooth. And same deal, we can see it on the position east graph. About 16 seconds, it hits that first waypoint, and the position starts to change to head to the second one. And same thing with altitude, it hits 200 meters, it looks like, and it starts to go to the second waypoint. And again, with the course angle, it starts to level out to travel to the first waypoint, and then it corrects to the second.
So kind of in conclusion with what we did, we were able to present an algorithm for creating waypoints and then also tracking those waypoints in a continuous system. So if the ship was not moving, you would just have set waypoints, but obviously the ship is moving. So you need your waypoints to update. And then from those updating waypoints, you need a way for the UAV to find out when it is at a waypoint to go to the second waypoint. So we were able to create a condition where if it's in a region of the waypoint, it successfully hits that waypoint, and then it moves on to the second waypoint, which is also going to be closer to the aircraft carrier. And then we were able to figure out a way to implement these outputs from the guidance system into our autopilot that we created, which would be the target heading, altitude, and velocity. Some future work that we'd like to do, we'd like to make the boat dynamics a little bit more realistic, add in some more factors there, so some degrees of freedom. And then we'd also like to create like an autopilot for the boat so that the user can input a area that you'd like the boat to travel to or something like that, so that the autopilot of the UAV can then follow the autopilot of the boat to land in a specific location. And then we'd like to generalize the code. So essentially the code does well, the algorithm does well for all situations, but there are some situations and cases where maybe it might not perform as well as in certain situations. We'd like to generalize the code a little bit more so that it performs well in all situations and cases in different courses. And then we'd like to have a smoother autopilot implementation. So you can see that the turning and the waypoint tracking actually was pretty smooth in those cases. But as you get the waypoints maybe closer together, if the aircraft carrier is moving slower, a UAV cannot make a sharp 90-degree left and right turn. So you get some very rigid turns and some awkward, not realistic UAV implementations. So we'd like to maybe make a smoother autopilot implementation with our guidance tracking system. And then the only reference that we really used besides what we did in class with the autopilot was just to get the boat dynamics, as the guidance and waypoint tracking system that we created was completely just on our own, and we just made that from scratch. And thank you. Is there any questions?
Thank you, Team 5. Good stuff. Judges, questions?
Hello. So you mentioned that you for your future work you want to improve the modeling on the ship. So I was just curious, what sort of a model are you using now? Is it like a point mass model?
Yeah, so essentially the ship is, just a point mass. So we just have a point mass kind of moving throughout, and then that's where the waypoint goes to. So it doesn't really have, so the final waypoint essentially is just a point that's like in the center of the aircraft carrier. So in the future, we'd like to make that, instead of a point mass, like an object volume, like I think it was Team 2 did. Or no, it was Team 1, I believe. So that essentially the ship, the UAV can then have a range of areas that it can land to and be a little bit more realistic with its converging.
Okay, thank you.
Okay, so for the ship, please go.
Go ahead.
Yeah, for the ship, you said that it's moving, correct? So, is it just linear, or I think, are you also considering any turning of the ship? Because while landing, there might be difficulty.
Yeah. So essentially, the ship does have turning capabilities with its 3 degrees of freedom. And the waypoint system, what it does is it technically puts the waypoints directly behind the ship. So if the ship were to turn, the waypoints would still line up. However, just in this case, the linear case is a little bit more realistic. Most aircraft carriers tend to kind of move in a straight line while the landing. So we just had it move in a linear action. But the ship does have capabilities of yawing with the waypoints.
This is Matt Romero. I have one question on your case studies. When you're starting on either the left or the right, did you have or did you guys run into any simulations where the UAV was too close to the ship and it wasn't able to make the turn and the corrections to get to the platform, or did you guys even look into that? Basically, my question.
Yeah, that's a good question. So that was just something that we basically looked into after we had this simulation done for our current case studies, because what the ship, the UAV is gonna have to do is, if it's too close, it's obviously gonna have to make a turn around, go back to those waypoints. So essentially, what we were working on was basically if you turn the UAV all the way around, its left and right turning is gonna be opposite of it moving in the positive north direction. So we had to change all the guidance systems to account for that condition to switch the left and right turning. So yes, it does have those capabilities, but whenever you turn around with our guidance system and try to go back to those waypoints, the longer the system goes on, the more simulation time you have. So the more constantly updating your waypoints. So the more I'm trying to see how to explain this. So the more updated waypoints you have along the timeline, the ship sometimes loses control of which waypoint it's going to. So when you do turn around, it does cause some issues within our autopilot, but we were able to get it to work. It just wasn't as smooth as just starting from behind it from a distance.
All right, thank you.
I have one question. So one is like orienting. Did you also consider velocity or how fast the aircraft should change the altitude? Did you check those constraints and put any constraints on that?
Yeah, so the guidance system outputs a velocity also to input into the autopilot, but you can see that whenever it slows down to change height and stuff, the velocity does slow down, and then it begins to speed back up again to match whatever it needs to catch up to the ship. So the ship's moving faster, it's going to speed up, but the velocity does change in according to if it's changing altitude, if it's rate of climb is climbing. So essentially, the velocity does change. The only thing I think that we would like to further do with that, which I think is kind of your question, is changing the velocity as it gets closer to the ship to land with a specific velocity. So like slowing down as you're coming into the land. For our case, it just kind of speeds up, well, it matches the speed of the ship to come in at a relative speed that's not going to be like too fast for the ship. But I think we'd like to maybe change the speed to land properly and slow down when it comes in to technically glide in, I guess, on land.
Okay. Any other questions?
One question I had more from the animation perspective, correct? So, it looks like you're seeing the aircraft from very far, like just like a point. Is it like possible to kind of zoom in on that so we're able to see the interaction between the ship and the and even the movements of the aircraft? You were saying, oh, it's taking a turn, or so right now, have you explored that aspect of it, like better visualization?
Yeah, so you can zoom in on plots just by zooming in, or what we have is as soon as it starts off as a fixed view. So it starts off in a fixed view, and then we just kind of rotate the plot. But we could change the view depending on, so like once it gets close to a waypoint, we can technically make a condition statement to change the view to zoom in on the aircraft or to zoom in on this. So we could technically make conditions at the waypoint locations to zoom in on those. That's not something we implemented, but we definitely could.
Okay.
And some of the initial teams, they're I think team 2.
Team 2, I think, yeah, there I think I saw a better, closer look of the view of the aircraft, right? Yes.
But yeah, okay. Any other questions from judges? Great, I think good job, guys. Pretty cool stuff. Thank you.
Thank you.
Thank you.
Let's have switch gears to aerial refueling, team 6. And your time starts now. If you're talking, you're muted, I think.
My apologies. I had my mic muted. Okay. Yeah. So good morning. We did aerial refueling of a UAV. I'm Isaac Poplin.
I'm Adam Bossy.
I'm Andrew Hermes.
I'm Will Hausfeld.
I'm David Doe.
All right, so this is just going to be a quick little brief of what we're going to cover today in our project of aerial refueling. We're going to cover going into what we did to understand the project, the problem formulation, what we did to set up the simulation, the results that we got, and then our final conclusions from the project.
So aerial refueling allows for the range and endurance of an aircraft's mission to be greatly increased. This maneuver is difficult and time-consuming, So our motivation for this project was to investigate methods of simulating and automating the air refueling. So our objectives here were to model the aerodynamic behavior of the fuel hose and drogue, command the tanker to follow a circular holding pattern, and guide a receiving aircraft to the drogue chute.
Some of the background work we did for this project was that we reused the UAV model from the class, so our dynamics files, Autopilot, and kind of all those files. And then we referred to several different papers on modeling and controlling of the refueling of the cord that were provided to us by Professor Sharma. And then we kind of just combined all these previous knowledge, all these models and papers into creating the scenario.
During this project, we were able to develop a controller for our receiver to track a rendezvous point on our drogue and then model our drogue or fuel boom based on the aerodynamic forces, lift and drag, and then create a autopilot circle holding pattern for our tanker and just adjusted our animation and our autopilot files from our previous work earlier in the semester. And then below is how we split up the work.
So as was mentioned earlier, the tanker and receiver model were reused from previous models created through the class with the help of Dr. Sharma and the class TAs. They account for the forces and moments created by the deflections of the control surfaces and then the different throttle on the engines. For the refueling cord model, we based it off of work in the papers listed here. Essentially, it models the tension between each node, the gravity forces on each node, and then the aerodynamic forces on each node. And then we also added an additional damping term to sort of simulate the loss of energy due to the stiffness of the cord as it's moving around. And you can see the formulas for some of those terms below. And this is the damping term that we added. It affects the acceleration of each of the node. And you can see a picture here of what the actual cord looks like when we simulate it. It's modeled it as a collection of point masses connected by massless springs, essentially. We used 10 nodes to model the cord. This was a good balance between realism and simulation time. As you add more cords, there's 6 states for each node, so obviously it grows quite rapidly and slows down the simulation to where it's really not useful for visualization purposes. And then you can see some of the other parameters we used in the model as well.
All right, for our tanker and receiver autopilots, as I said before, we used our work from the semester, which would allow us to control and hold a steady flight for each aircraft. But something we changed in our receiver aircraft was our altitude control, throttle control, and course command, where the altitude would just take the altitude of our cord or fuel boom and have our receiver aircraft match that altitude, while our throttle would take a distance or our vector between a position on our receiver aircraft to our fuel boom and divide by 10 to get a certain velocity and just add 35, which is our current tanker velocity. And the course controller, we would take the positioning of our fuel boom and find the angle between the receiver aircraft and our position using the formula below, and that would be our course command hold angle.
All right, and then the simulation setup ended up being quite beefy with 2 very large autopilot simulations, one for the tanker, one for the receiver. We used MATLAB and Simulink to model it, and then we read the data from our tanker and from our cord to develop those tracking functions and put those into MATLAB, and those fed into our receiver aircraft autopilot. And so the receiver is omnipotent. It has a perfect knowledge of the states of the drogue chute, and it makes sure that it gets to that point as best as it can.
So going into a little bit more detail of each of the sections here. So the first section at the top is the autopilot for the tanker, and this just generates a circular course, so the tanker will slowly fly in a circle in the air. And then the velocity of the tanker is fed into the dynamics function of the refueling cord, so it can calculate how the cord behaves dynamically as the airspeed changes. And then, as was mentioned previously, the receiving aircraft has perfect knowledge of the states of the drogue, and it uses these states to calculate the direction it should fly, the altitude it should aim for, and then the velocity. And then all of these states are bundled together and fed into our simulation file to actually draw out the simulation. And this is what it looks like when it's running. The top left is the actual visualization. Top right is the states of the receiving aircraft. Bottom right is the states of the tanker aircraft. And then bottom left are the relative states of the drogue chute. And you'll see as it starts to approach the tanker, the commanded velocity of the receiver will start to slow down and it will eventually match the tanker. And the stuttering you see in the simulation, as other groups have mentioned, is just due to the complexity of the models, the number of vertices and states we're using. It's tough to render this in real time. And this is actually sped up a little bit so that 1 second of simulation time is roughly 1 second of real time.
Here's a better look at our tanker state variable plots.
And here's a slide of our receiver state variable plots. You can see that our values pretty much even out towards the commanded values. And as for our discussion, our simulation pretty much went as expected. Our receiver was able to locate the chord and hold for a certain amount of time. Our flight path and controls all showed expected behavior. And kind of our limitations that we were faced with was timing. I mean, we only had 3 weeks to simulate something very complicated. If we had more time, we probably would have gone with more, stronger wind or more of like a mass transfer system or etc.
Overall, we're very happy with how the simulation turned out, but some concluding remarks would be that constraints on time result in some of the physics being neglected. So that's the vortices from the tanker, mass fuel or mass transfer of the fuel. So this doesn't take away from the success of the simulation, but it does reduce the realism quite a bit. The physical dimensions of the aircraft differ from the true scales, which could result in the dynamics of the aircraft being affected. And the difficulty of aerial refueling was shown through a lot of the complex development of the autopilot systems. However, the resulting simulation shows the possibilities of what could be accomplished, and more realistic models and physics can be added on top of the existing simulation.
With that, that concludes our presentation. Thank you to everybody for coming out this morning. And are there any questions?
Good stuff.
Good job, guys.
Sure
I have a quick question. If you go to your previous slide, the conclusions, yeah, this one. It's not a question, it's a comment. In general, if you want to mimic the physics which might happen because of the size, shape, velocities, whatnot, one of the things which you can leverage from your fluid dynamics courses is the concept of dynamic similarity. So for example, Reynolds number, if you basically choose your forces based on what expected Reynolds number might be, that might give you a much closer solution than actually thinking of doing the real scale things, right? So that's sort of the usefulness of some of those things that you've studied in your classes. But other than that, good job.
Thank you.
Thank you very much.
Matt,
So
Krishna.
yes, I do have one question. If you go back to your model, your slide with your model.
The Simulink model?
Yeah, the Simulink model. Thank you. Looking at that on your actual diagrams, you calculate or you're calculating for velocity. Are you calculating for adjustments of altitude as well, of both the UAV and the fueler?
You mean like different densities from altitude?
Yes.
Yeah, we're just simulating a constant density right now. That could be added later on, but for time constraints, we picked constant density.
Okay, thank you.
So one question I had was, so it's a moving aircraft. So do you do the analysis in the relative velocity space, or the target is just it has to reach a moving target speed? right? Sorry, the non-zero target speed, right? So and relative velocity is always like, or like, in missile guidance we have this line of sight planning, right? Path planning. So where you consider the relative velocity between the two moving objects.
Right. So basically, how we're calculating the differences between the states is each basically object in the simulation knows its states in the relative frame, or just where it's at the body frame. So we convert those to an inertial frame, and then do all of the relative stuff relative to the inertial frame. So it's all with respect to the origin of the simulation.
I see. Thank you.
Could you explain a little bit more about the drogue chute modeling? Like, how do you get the states?
Yeah. So basically, I don't know if you can see my mouse, but we're simulating it as it's a collection of point masses. So each of these points here has mass, and that's where the aerodynamic effects are applied. And then there's tension forces, which are applied in the direction of the links. The tension forces are calculated as an elastic spring. So this is the Young's modulus and the cross-sectional area. And then this term here basically calculates the displacement between one node and the next. So that determines how much the displacement is to how much force should be applied in each direction. And then the velocity or the aerodynamic forces are calculated here. And these coefficients just determine the direction. The drag term is applied on the opposite direction of the velocity, and the lift term is applied perpendicular to the direction of velocity and the direction of the chord. The only inputs, the only.
Okay. Yes, I was just concerned about how you were putting the aerodynamic forces. I missed the point where you have the different masses connecting. Okay. Yeah. Thank you.
Any other questions? This was a hard problem. These guys went over the Journal of Guidance papers, and so pretty commendable stuff. Good job, guys.
Thank you very much.
Thank you.
Thank you. So let's move to Team 7. I think that also is aerial refueling, I believe.
Yeah, we're also aerial refueling. Can you guys hear me and see my screen? Okay.
Yep. And your time starts now.
Okie dokie. Alrighty, so as Dr. Sharma just said, we also did aerial refueling of UAV systems. My name is Nick Osterish.
I'm Evan Osman.
I'm Asant Abzwari.
And I'm Ethan Verkwer.
Yeah, I'll just be running over the table of contents with everyone really quickly. So we're just going to go over a brief introduction of what we did, touch a little bit about the background and the assumptions that we made. Then we'll talk about the contributions to the actual modeling that we did, the things that we put in our MATLAB. And then we're going to be talking about the problem, what we thought would be a good solution to the objective of aerial refueling. We're going to look at the control objectives, how we set up the simulation, and then wrap it up with the results, discussions, and some conclusions after that. So a little introduction. So aerial refueling is a large part of the U.S. military operations. It requires to extend the range and time that an aircraft can remain in the air. So this problem can be met by increasing the fuel efficiency, tank capacity, and other factors along those lines. Another solution is aerial refueling. Aerial refueling, when we were doing a lot of reading about this, it requires precise handling for both receiving and host aircrafts. And at times, the videos that we watched and the papers that we read, that these maneuvers can be done at the harshest and most challenging of environments. Aerial refueling also saves time because the aircraft does not have to land. So, and at the end of the day, this results in more lives saved and missions accomplished, becoming a key factor to increasing mission success and saving lives at the end of the day. A large case study was the C-130 Hercules, which has been a standard for tactical air refueling for almost 60 years and is utilized in a variety of applications. So the hose and drogue is what we utilize here in our MATLAB simulation. Sorry. So the hose and drogue is what makes air refueling possible in our MATLAB simulation. With the mothership aircraft, the tanker, the actual aircraft possessing the fuel, flying ahead at an elevated position, and the receiving aircraft flying behind and lower. If you want to go to the next slide for me. So I'm going to talk about the two different methods of air refueling. I was reading a paper from Lockheed a few days ago, and they talked about two main methods, and these are the two main methods that Lockheed described that the U.S. Air Force used. So they used a flying boom, where a boom operator lowers obviously a boom from the body or the wing of the aircraft, and the receiving aircraft sort of ushers itself into the boom, and the aerial refueling occurs there. And so conversely to that, the alternative method that Lockheed mentioned that the U.S. Navy typically uses, and what we used here, was the hose and drogue system, where a hose extends from the aircraft, and a chute-like system is also extended so the aircrafts can refuel. And the C-130 case study that I was talking about is in the picture in the top right. And this is obviously refueling a rotary craft wing. If you want to look at the bottom left, that gives a really nice close-up view of the hose and drogue method, and to the right of that is a great visual of the boom operator method. And some contributions that we made to the project is we showed that two aircraft, a tanker drone, what we call the mothership here, and a fighter aircraft represented by CAD files. So in a three-dimensional space, showing refueling capabilities and in the interactions between them during flight. So we use a combination of STL importers in MATLAB, populating the leading aircraft in our animation, along with a drogue used to extend fuel from the tanker to the receiving aircraft. So the receiving aircraft was created traditionally in MATLAB, and as was the drogue. So we modeled the drogue how we typically model things in our earlier class assignments. I believe it was touched upon last presentation as well. We'll be going with the drogue a little bit more in our later slides. And the graphs here that were produced independently of one another, it basically modeled the XY position of the mother aircraft, or the tanker, as I've been referring to it. And we also have a plot here referring to the XY position of the drogue. And above that, we have all four bodies interacting in relation to each other in the simulation as a whole.
All right, so I'm going to go over the related work. So as Hassan kind of mentioned, and the previous group mentioned, there's quite an array of existing work out there on aerial refueling systems and drogue modeling. We mainly refer to 5 references, the most important being reference 4 and reference 5. This is where we got the vast majority of our mathematical modeling from, which is our MIT Melbourne and Brigham Young University. So our team's work came in translating these equations to a working MATLAB code, and then also making sure that we had a visual representation of what was actually being calculated. So as far as the modeling goes, the general methodology here is that you have a refueling hose, which is modeled as a series of point particles. We chose n equals 5. If you choose number bigger than that, you start to get more realistic, but the simulation definitely starts to lag a little bit. We went with the total mass of 1 kilogram. And each one of these point masses is connected by a rigid spring link, which is massless, and that has a spring constant of about 0.05. Links 1 and 5 up here at the top are mated with the mothership and the drogues, respectively. And then the drogue at the bottom is modeled as a separate point. We did a 3D CAD model with a 2D circular cross section meeting the free stream, so just essentially drag over a circular 2D plate. We went with an area of 0.25 meters squared, mass 5 kilograms, and its initial position was just directly under the ship. As far as our other assumptions, we assumed about 1 kilometer altitude, temperature about 280 Kelvin, density 1.253, and speed of sound at 340. The UAVs, we had the mothership at the top, level flight, constant velocity, constant altitude, and then the MAV at the bottom, which is the one that was controlled and had a variable velocity, variable pitch and roll, so it could catch up to the top. I'm gonna brush through these equations real quick. I'll spare you guys some of the mathematical complexities, but essentially we use Gauss's principle, which means we can define the forces, accelerations, and positions and masses for the entire series of point particles. The actual acceleration that is realized is equation 2, where equations 3 and these two matrices are what go in here. And then there's quite a lengthy derivation, but the equation we actually end up solving is equation 9. This is just some more. These are the coefficient of drag and coefficient of lift models. I won't cover these too much, and I'm going to hand it off to Evan.
Okay, so Nick briefly touched with the Gauss's principle. That was derived in Resource 4, the Brigham Young paper, and our equations were directly referenced from our code in that. And then I want to talk a little bit about the controllers we used. So the main application of a PID controller we had in our code was when we were telling the receiving aircraft what to do. And so eventually what our code was able to do was have the receiving aircraft recognize where the drogue was and try to track it and actually connect to it. And in order to do that, we needed the PID controller. Initially, we were intending to maybe put one on the mothership to enable it to react to environmental factors, maybe such as wind gusts. However, due to time constraints, we were not able to do that. So there is an opportunity for further implementation there. We briefly tried to use a Kalman filter. However, we quickly decided to not after running into many issues, debugging and logically working through it, and just was unnecessarily complicated.
Right, so here we have the Simulink. The top shows the overall structure where we have a subsystem block for the mothership controls, the drogue controls, the cable and drogue dynamics, and the MAV. And then also the plot where we actually display the animation. And the bottom there is the subsystem of the cable and drogue dynamics as an example of what these subsystems look like, where it takes the mothership states and the drogue control states, runs it through the code, and outputs the drogue states and the cable states.
Okay, let's take a look at our results here. So we can see that the mothership starts to accelerate, and then you can see each point mass following, and eventually we'll bring the drogue along with it. And you can also see the receiving aircraft start to fly towards the drogue, and then eventually here it should catch up. And then it will be able to recognize when it is within distance of the drogue, and then you will be able to see them connect here. And there it's refueling. Okay, and then here are a couple plots we had. You can see on the left is the mothership XY motion, which traveled over 300 meters westward. And then you can see that the drogue didn't go nearly as far because it had to account for the hose length, and each point mass didn't quite accelerate at the same rate the mothership did. Eventually, they would have become closer since they would be traveling at the same velocity, but our video did not go that far.
So we are over time, so I'll just give a brief explanation of this. So basically, throughout the duration of this project, our scope has narrowed a bit. We haven't done any of the advanced things we were planning on, such as mass exchange and wind gusts, but we did do the main things we were hoping to do, which was the hose and having multiple points so that the cable actually bends and the receiving aircraft follows the drogue and attaches to it. So go ahead to the next slide. So what we would like to do moving forward is to include those complexities and then also incorporate the Autopilot file to make both of the aircraft fly within Autopilot. and then add in the mass transfer and a visual environment.
Just some large scale lessons learned. Project management, make sure we spend more time defining the project than actually doing the writing, and it'll make things go quicker down the road. And then technical lessons learned, we discussed them. And I think the next slide is our Q&A. So if there's any questions, I'll open the floor.
Thank you. Yeah, questions? So maybe I'll go. Yeah,
Oh, yes, Dr. Sharma, go ahead.
So in your simulation, the cable was like looking like it was not connected to the mothership. Is that like, what was the reason?
So the reason for that is how we imported the STL. It puts the position of the aircraft at like the top right corner of the whole STL instead of on the actual aircraft itself.
Okay. You repeat, so it's a repeat of the mistake.
Yeah, if we had more time, we would have found a way to adjust that to make it connect.
Yeah, we kind of got bogged
Are
down.
you making a rigid assumption of the host, or is it flexible?
So we went with the rigid assumption. So basically, it just has a defined length, and essentially with the spring constant, that basically accounts for the dissipation of forces across the point masses.
Okay.
You all mentioned that you had an idea of incorporating a Kalman filter. So I was wondering what exactly was the idea of trying to use a Kalman filter for?
Ethan, do you want to get that? Or do you want me to?
You can take that one.
Okay. So the idea with the Kalman filter was essentially in class we learned how to do integral controllers, derivative controllers, and then PIDs, which is the two of them combined. So we kind of wanted to see, you know, is that used in the real world? And from our research, we found this thing called the Kalman filter, which is kind of the overarching concept that's used in controlling spacecraft and aircraft. We tried like a really simple model. For everybody who's not like super familiar with the Kalman filter, it's basically constructing Gaussian distributions of where your vehicle could end up, if that makes sense. I don't know if that's like a proper explanation of it, but it was just an idea that given a lot more time, we would have been interested to flesh out.
So I think basically you were assuming that you know all the states and how could you determine where the hose is, and so basically state estimation rather than control.
Yeah.
Okay. Awesome. Any other questions for team?
I don't have any.
7. So what we'll do is we'll take a 5-minute break. I think everybody needs a break. So we are kind of halfway. So let's reconvene in 5 minutes if you want to take a nature's break or whatever you want. Maybe grab a banana or apple or something. Okay, so we'll it's 10:11, so let's meet at 11:05. Again, means we'll keep the call on if you want to talk, and that's all right. But yeah, so team 8 will go next at 11:05. And so I pasted this naval survey, ONR naval survey. So if you guys, did you guys see that, the link that I've sent on the chat or Teams?
Yeah, we were able to get the link.
Okay, great. So yeah, so far I think you guys are performing really nice and awesome. I'm proud of you, everyone. So let's keep going. So yeah, let's do at 11:05. I'll grab maybe a coffee or something. And is that okay, Prashant, Matt, Anushna, Krishna?
Sounds good.
Yes, yes.
That sounds good. Raj.
Hey, Krishna.
Oh yeah, sounds good.
Okay. Okay, welcome back. Generally, when we meet in person, generally I order pizza for the class and we all have fun there, but different times. Hopefully that time will come soon.
Yes, I hope so very much.
So,
well, I'll take a rain check on pizza. Just kidding.
Yeah, those were good times. But yeah, even though it was a virtual class, I think we had lots of fun. We tried everything to make it as similar level of what we do when we do classroom teaching. Okay, let's team 8. You guys can share your screen and we'll go from there. And this is also aerial refueling. Your time starts now.
All right, so we're team 8. We did the aerial refueling as well. Our team included Matt, John, myself, Graydon, and Caleb. Matt, you can go to the next one. This is just a rundown of our table of contents, what we cover in our slides. Next. For an introduction, aerial refueling is a very complex multi-system operation that requires precision from both planes involved. It's really helpful for allowing missions to carry on for longer durations, so planes don't have to land to refuel. With drones coming more and more into the Navy and Air Force and everything, we figured that we could automate this process and make it more of a computer thing than a pilot-operated system. We ended up using a flying boom. With the time that we had, we ran out of time to work with the resources we have, so we ended up with the more rigid boom style of refueling. In this scenario, though, there is a boom operator. We figured that we could either automate this process or have a boom operator working from the ground, either with a VR type of headset or just a screen. So our objectives for this final results, we wanted to incorporate both of our aircraft into one animation as well as our drogue. We wanted to model the behavior of our receiver so that it would navigate to the refueling location, and we wanted to be able to carry out a full refueling mission. So the contributions for our animation file, the main additions we needed to do were get both of our models into one animation so that we could see them working. With our dynamics, we used the same models that we had from the previous assignments we've been using throughout the semester. For the autopilot files, we used the same one for our tanker drone, which would be the leading aircraft, and then for the receiver autopilot, we had to incorporate a lot more states that would read off from the tanker so that we could close the gaps between them using our codes and cases that we developed.
Okay, so these were some papers that were provided to us so we could complete our project. That is the flight control and simulation of aerial refueling and the modeling and simulation of hose paradrogue aerial refueling systems. From this paper, we utilized the idea of reference frames, and we configured this to our autopilot to allow the receiver aircraft to know the positioning of the tanker aircraft at all times. We'll touch on this more later. As for gaps or limitations in our model, we weren't able to get to the inertia changes as the fuel gets transferred between the tanker to the receiver, along with the aerodynamic effects from the tanker on the receiver and the aerodynamic effects and physics of the drogue from the tanker. As for modeling, our C-130 or our tanker autopilot, the tanker autopilot is actually very similar to our old homework assignments. We just had to tune some of the gains to get our tanker to fly properly. As for the receiver autopilot or the F-18, we were actually passing all the states from the tanker into the receiver That way the receiver plane knows the positioning of the tanker at all times. And you'll see later how this wraps into our autopilot. The receiver is able to change course using the various states we have implemented, including position north, east, down, and our velocity states. And as for the drogue dynamics, like Ben said earlier, we're going to be utilizing the boom drogue system instead of our point mass drogue system.
So our main objectives for control was just to keep the tanker going in a straight path smoothly and have the receiver get those states from the tanker and the drogue and track to it with our 6 velocity cases, 4 altitude cases, and 5 course cases that tell the receiver to speed up or slow down in a given direction based on its position relative to the drogue. Next slide. So these graphs are a visual representation of that. So you can kind of see as we're getting closer, distance-wise, we'll go from fast approach, standard approach, slow, and then velocity hold. And similar setup with the course and altitude. And so for our Simulink setup, it's similar to what we developed throughout the class for the tanker dynamics and autopilot, but then you can see it's looped around back into the receiver as well as animation, and then they're both animated at the same time.
Matt, you're muted.
Thank you. There we go. Talking about the results, which we'll show in the videos, we were able to achieve our control objectives of the receiver approaching the tanker, staying at the position of the drogue, and then backing off once it's done the refueling after a certain amount of time. And then a note about the parameters, just that all the parameters were the same for the most part that were used in the previous assignments, with the exception of the new zones that Caleb was talking about, so the velocity zones and the course zones. So here is the first simulation, which is just with no offset, so it's at a different altitude than the tanker, and so it has to climb to reach the altitude and then do the process. It goes a little quick. And then once it stays there after a certain amount of time, it'll back off like that. And then for the animation, sorry, I'm going to go back real quick. We did have STL files that we were going to use, and after running the simulation, it just took way too long. So we just used the simplified models for the animations and the videos just to speed things up. And then here are the plots for those cases. So on the left is all the states for the tanker, and the right for the receiver. So you can see that on the left it achieves the altitude and then just stays in that position. And then on the right, there's some more disturbances because the receiver has to match the tanker, but it does still steady out and converge and do what we want it to do. The second case was the same thing, but with some offset. So it's at a different horizontal position first, so it has to adjust the course angle. So you can see that first it achieves the height, and then it moves over, and then it speeds up. And then falls back again. Here are the plots for that case. So the tanker does the same thing, so those all look the same. On the right, there are some more disturbances because of the added complexity of the course change. But again, it does still all steady out and do what we were looking for it to do.
All right, to discuss a little bit about what we've done, as you can see with our models there, that we were able to get to link up with both an offset and without an offset. However, there are some limitations to our modeling pertaining to it does first align with altitude, then align with course, and then with velocity and position. However, if the tanker would move during that time, our model would struggle or unsuccessfully try to reach the drogue position, as well as I want to touch on a little bit of computing, as you can see with our video. We did very simple models for demonstration, but if we were to use our STL files, it would take 10 times the time to run. And we thought that that would be an issue and a limitation with our overall model. So going into more of our conclusion here, next slide. Yeah, so again, even though we were able to do it, we weren't able to do things because of time constraints, including that point mass that we've seen before, as well as the change in mass in both aircraft as the refueling process begins. Given more time, we'd focus on the point mass approach and possibly implement, instead of a boom assumption, we'd implement an actual dynamic drogue that would also affect the tanker's path. And so we'd use the tanker autopilot for that. We were preparing to do that, but unfortunately, due to time constraints, we weren't able to. Also mentioning in there as well, both aircrafts are burning fuel and are also transferring fuel. So there is some mass distribution that changes during the autopilot phases. So we wanted to factor that in as well. But overall, we were able to accomplish the model that we looked for. And next slide. We will open the floor to questions.
Thank you. Right on time. Questions?
Could you explain what is a boom drogue? I'm sorry, I don't know it. So could you just explain what's the difference between a boom drogue and a point mass drogue?
Yeah, I can cover that. So a boom drogue, or a flying boom as it's known, is a more rigid type of refueling. So as we've seen from the other groups, they have the hoses with different points along the hose being having a weight given the point mass system. And those sections would adjust with the aerodynamic conditions that are being given the code. We did not end up getting a successful boom drogue or a successful hose drogue, so we figured we could use a more rigid system so that our planes could be fixed more or better, so to say.
Okay, thank you.
Yep.
So this is Matt Romero. Yep. So you guys considered the weight distribution between both planes, but you guys considered a wind and how that would be affected for both, and potential upgrades or changes to your models based off of that.
So in those videos we didn't account for wind, but they are accounted for, like we were saying, because we used the autopilot from the assignments, and from the assignments we developed the abilities to consider the wind. So there were 0 in the videos, but we could just add those.
Okay, so did you guys try any trial runs or just try to play around with it and see what you guys got, or that was just something for future?
Yeah, we did not. That would be something for the future, which I may
thanks.
try right after class, actually.
No problem.
Any other questions? Okay, then let's thank you guys. Good stuff. Let's move on to team 10.
Thanks.
Thank you.
Okay, your time starts now.
All right, good morning, everybody. We are Team 10. My name is Brady, and I worked with Noah, Thomas, Jacob, and Zach. And we did our project on the modeling of a fixed wing UAV landing on a moving ship. So this is just a brief summary of all the different topics that we will be discussing today. And then just to give a brief introduction, obviously unmanned aerial vehicles are rapidly growing in popularity in multiple different industries. The use of UAVs are prominent in the Navy, and a current challenge is landing one on a moving ship, and this is due to the relative motion between the UAV and the ship. So when you have a pilot that needs to land on a ship, they can usually rely on their skill as a pilot in order to predict changes in the ship's motion to find a safe time to land. But obviously a UAV doesn't have this human capability, and they need to rely on systems that include GPS, radio frequency, and sensors in order to
Just
orient
for
the...
1 second, I think I said team 8 to team 10 directly. So judges, make sure you'll grade team 10. This is team 10.
All right.
Okay,
But yeah.
Thanks for letting me.
Oh, my bad.
Okay. Yeah. Team 9, sorry, you will go next.
But yeah, all right, next slide. And then for our project, we wanted to animate an aircraft carrier and a fixed wing UAV, as well as correctly model the dynamics for the two. And our end goal was to have the UAV autonomously land on the aircraft carrier.
Jacob, you're muted.
Thank you. So the contributions for this project were that we were able to animate both a fixed-wing UAV and an aircraft carrier. We used STL files for both of those and populated that into the file, which then created a 3D space representation for them. The dynamics file for our fixed-wing UAV was taken from our previous assignments, and we had minimal modification, if really any, with that. And the autopilot that we used for our previous assignments as well was the file that we have been primarily using for this project. For the ship, though, the dynamics file had to be created from scratch, and we were able to do that using the paper that Professor Sharma provided us with. In terms of modeling, we wanted to implement GPS usage into the UAV so it could calculate relative position between the two bodies. And at each time step, the data updates so we can have the most accurate course, and the UAV can correct itself if any unfavorable conditions are experienced. We used the UAV textbook that had the equations of motion in it, and we were able to integrate those and ensure that our plane was flying properly. And then our ship model was based off, like I said, the paper provided. And some things that we did with the ship in specific were it was moving at a relatively slow velocity, around 20 meters per second, and it was primarily moving in a forward direction, but it did have sway and things like that implemented into the file. And for our objectives, we were to put the aircraft carrier at a forward trajectory at a constant speed. And with this being the case, the UAV was able to, like I said, take that data between the two bodies, and with the aircraft carrier moving at a relatively slower speed, the error was mostly due to the UAV, and we also implemented error filters, so we didn't have any unfavorable results. And we also wanted to give the UAV a predetermined flight plan using a series of coordinates, such as a climb in a spiral, and then a cruise, and then it will finally come back to its descent location. And yeah, so to do that, we would have to calculate relative position again, and then find the optimal descent path.
Somebody's muted again, or I don't know if you're talking.
Thomas, are you muted? Okay, well, as you can see here, we have our simulation set up with some of our Simulink files clipped in. and the lines are connecting the states and how they would transfer through the different Simulink files themselves. Over here we have our waypoint finder, which are GPS, and that then trickles down into most every other aspect of it, going into the autopilot, and then the autopilot down here, and then into the dynamics, and really every other aspect. You can see that there's a chain of connections.
All right. Can I be heard?
Yes.
All right. Fantastic. Sorry about not being audible on that last slide. This shows our waypoint or our simulation. Due to time constraints, we were unable to properly simulate the landing of the UAV. However, we were able to run a simulation displaying the functionality of our waypoint system. This is the simulation depicted by the footage shown here, which has been sped up by a factor of 10. And if it completes at the clip shown when sped up by a factor of 10, shows you how long it would have been otherwise.
Yeah, so there were our results. We got the ship to move, and the ship was moving in one direction, and we also got the UAV to be able to follow that and change its flight path according to the movement of the ship. We are just a little bit short in putting it all together because of, time constraints, much like many of the other groups. That brings us into limitations. Of course, time was a substantial factor. We really believe that we were really close to figuring everything out, and given an extension of not too much time, we think we could have been able to complete our simulation and land the UAV successfully. We accomplished almost everything we set out to do, but the integration of the waypoint equations required some more refinement and attention. But again, time constraints, so we couldn't quite get there. Conclusions. Like I said before, we completed almost everything we set out to do. We got both the UAV and the aircraft carrier modeled within the same animation file. We got them to perform their individual dynamics. We got the UAV to move the way we wanted it to for the most part, and then we got the ship to move constant at a forward velocity. We got the equations of motions were integrated correctly into the models. As far as improvements are concerned, it's really back to those waypoint equations, further refining them and implementing them so that we could complete all the other work that we had done correctly. Thank you.
Okay.
Any questions?
Questions?
So what was the rationale for using a spiral path for the landing of the aircraft?
That wasn't necessarily for the landing. That was mostly just to showcase how we wanted to have a predetermined flight plan where the plane would then carry it out.
Okay. Thank you.
Like if you could do spiral path, which is complicated, means I don't know, like landing path would have been easier as well.
We were also trying to get it to where we could take off from the boat as well. So the spiral path would allow it to spiral up to a certain height and still be around the ship and then come back down in a spiral path in a relative distance from the aircraft carrier.
Other questions?
How much time did you guys spend developing the initial requirements or what to work on first as a team?
Yeah, I think that part is where we really struggled at, is we didn't take enough time to develop like the requirements and what to actually like split up and like work on, because it was hard to think of a way to split up like the program files and stuff to where we could efficiently get things done.
Okay, thank you.
Other questions? Okay, thank you, Team 9 or Team 10. Sorry, this is Team 10 judges. Okay, so Team 9, you guys up now? Sorry for the mix-up.
No worries.
It's okay.
I'm gonna share my screen real quick.
Okay, your time starts now.
Okay, this is Team 9. For this project, we decided to land a UAV on an aircraft carrier. I'm going to pass it off to Ethan Grayson to get us started. You might be muted. Are you guys able to hear me?
Can you hear me now?
I
can.
can. Yes.
Yeah, we can
Okay.
hear you, Ethan.
Okay. Here's a quick overview of the contents of the PowerPoint. The project objectives, the background, the problem formulation, the control, the simulation, the results, the discussion, and the conclusion. The main goal was to create an autopilot capable of safely landing on a moving target. To do this, we needed to create a parameters file detailing the individual aircraft, the animation in order to show the interaction between the carrier and the aircraft, simple ship dynamics, the aircraft dynamics, which we were able to pull from the assignments we were working on the entire semester, and the big thing, which was the aircraft autopilot, which would direct the plane from point to point. The related work we basically based a lot of our work on was a report by a Linnea person on the cooperative control for landing a fixed-wing unmanned aerial vehicle on a ground vehicle. We just replaced the ground vehicle with an aircraft carrier. Existing systems depend on GPS and sensors on the runway for more precise information, such as exact height from the runway. And our model is supposed to simulate a GPS-guided system with the addition of the current course setting for both the aircraft and the carrier, so that the aircraft can align itself with the runway. Practical applications. First off, it's an autopilot capable of flight and landing of a UAV. More specifically, it's capable of moving up to a landing on a moving target, whether it be a fighter onto a carrier or a drone onto a blimp. That'll just be a simple change in the parameters for the aircraft. And it completes our work over the semester for a fully functioning autopilot. And for a actual manned landing, this would be very useful for like a safety system, as landing on a carrier is a very dangerous task. And this could simply just say whether the incoming velocity or height was safe enough for a landing.
I'm going to take it back over for the modeling. As we said before, the primary objective is to create a autopilot capable of safely landing on the moving target. In order to complete this project, we had to make a few large assumptions, such as the autopilot always knows the location of the target and itself, along with the course heading of the target. Also, we had to assume that the target moved in a straight line at a constant speed and remained level. We definitely experimented with more complex models. However, we couldn't get the autopilot to work correctly with those, and so for this final presentation, we had to opt out of that. Also, the wind is turned off during our simulations, but we do have it implemented within the Simulink model, and so it can be switched on. As far as the animation goes, we are able to import STL models for both the aircraft carrier and the UAV. And upon landing or reaching the edge of the deck, the view does switch to an automated landing view to give us a better picture of the UAV. I'm now going to pass it on to Michael.
Okay, for our dynamics, we're using a simplified dynamics for the aircraft carrier. So our assumptions for that are that the water is undisturbed by the aircraft carrier. So there's no like waves crashing into the hull and creating like a roll moment or any complicated motions. We're assuming that the aircraft carrier is level to make it easier for the aircraft to land. For the unmanned aerial vehicle, our dynamics are based off of our previous assignments. We have our dynamics from the UAV textbook based on a fixed-wing aircraft. And for the autopilot, we have 3 inputs for the autopilot. So we have the initial airspeed, course, and altitude. From there, the autopilot uses waypoint navigation to find the target position and iteratively descend to an optimum level for landing.
Okay, so for the waypoint navigation, we decided we wanted to modify waypoint navigation a little bit. So instead of reaching a specific point, we want to reach a specific point at a specific course heading. So to do this initially, we create a vector opposite direction of the course heading of the boat, and then we multiply that by a distance d. We chose 150, and that created a boundary point. And then from that, we created another vector orthogonal and created 2 more points far off. That created a line, which makes a boundary line. So when we're on zone 1 on the other side of the line, we will fly opposite direction of the boat towards the line. We can determine which side of the line we are. We're using that d of xy function there. When it is positive, we are in zone 1. When it's negative, we are on zone 2. And when it's 0, we're on the line. Here, go to the next slide, please. So once we are over the line, every iteration we are going to calculate a circle that has a center along v hat, which is the vector orthogonal to the chi of the boat, and has 2 points on it, each of radius r, one at the p-bound and one at our current location. This allows us to, if we always follow the tangent of the circle, to arrive at our boundary point with exactly the course heading we want, plus or minus about 0.5 degrees. So the way this is calculated is we just create a vector between p-bound and our current position. And then using a general isosceles triangle, once we calculate the angle between C and p-bound, or the vector between C and p-bound, we can calculate theta, and then we can calculate the radius. From there, we just have to find the center location, which is C-bound, or C equals p-bound plus v hat r, and then that can simplify to C equals p-bound plus v hat s over 2 cosine. From there, we can create a vector from C to our current location, which would be x minus cx, y minus cy, and then we can just translate that vector 90 degrees, giving us y minus cy, cx minus x. We do have to take into account which cases we are in. So like if we're going the opposite direction, we need to flip it 90 degrees clockwise. Or counterclockwise. And then just to get our desired course heading, we just take the arctangent of the y component of the a vector and the x over the x component of the a vector, and we subtract that by pi in this case. Once you passed east or west of the point, you have to you could drop the minus pi term, and then that'll get us exactly to p-bound, and then we just fly directly at the plane. So here you can see it in action. We chose a pretty far out distance just to demonstrate it well. the path it will take. Did it freeze for everyone else too?
Yes.
Yes. Bailey, can you like switch slides forward and back or something to make it unfreeze? Oh, I think actually Bailey froze.
Does anybody? Okay.
So basically, it's going to follow a path until the current boat's heading is 10 degrees, and it's going to follow a path at 190 degrees until it reaches that boundary line. It will rotate in a circle and then approach the boat from behind dead on. Here, I can pull up the PowerPoint, and then if you make me the host. Sorry about this. Or not make me the host, but give me permission to share.
You have, I think everybody has permission to share.
Okay.
So yeah, last 1 minute, if you can wrap up.
Yeah, we can be really fast from here on out. Oh, no. Okay, here's the animation in action. As you see, it goes negative course heading until it hits the boundary line, and then it rotates around and approaches the boat from behind. You're a little low on time, so I'll just cut ahead once it faces it. So yeah, now it's going directly at the boat. Okay, off to Michael.
Sorry about that. For the control objectives, I'm gonna have you guys follow along with how we did the compute gains for the autopilot. So for each of these little tables, we have each of the loops for each of the gains, and these are just showcasing the optimum values that we use for the autopilot. So for each loop, in the bottom, we have like a picture of the model that we use to determine the stability of these loops with these optimum values that we discovered through iteration. You can go to the next slide. And for the video we have showing, this is our earlier model. You can notice it gyrating like up and down. This happens because our models are scaled down way smaller than what we computed the autopilot to be able to do. So it has to land in a more precise area behind the boat, like right near the edge of the runway. As you can see, it touches down, and it will continue to move with the boat. It will stop and catch on to the anchor, which we also simulated. And to the left, we have some plots describing the motion of the UAV during the simulation time.
So I think we'll cut it here. So we'll directly kind of go to questions now.
Okay.
Thank you. Questions?
Did you consider different speeds of the boat, and and also what were the speeds involved?
Speeds of the boat. For the pathfinding, the speed of the boat isn't a very large issue because since it's updating that circle iteratively, as long as it is, the circle you'll still end up at the correct point, and then you'll be going directly behind the boat. So it's just a matter of fact of going faster than the boat to catch up because you're going with the same course heading. It's really turning where it runs into an issue.
Mhm. In terms of absolute values, like I was just curious what speeds you used in your simulations.
For the UAV, we're usually flying at about 35 meters per second. And for the simulation show, the boat was actually fixed, but I had tested it with about speeds up to 20 meters per second, and it would still work.
So this derivation that you did about the circle, was that taken from some papers or you came up with it?
I mostly came up with it. A little bit of just reading articles about like analytic geometry and stuff like that. Because I mean, it's nothing too complicated.
Yeah, good stuff. I'm very impressed, like the amount of technical or detailed derivation you have done there on your own. So that's good stuff.
Thank you.
Other questions?
Could you go back to your final results slide?
This one?
Yes. So right on the left-hand top, where you have the plots, what is the second last row on the left column?
I believe that is our thrust.
That is the elevator, actually.
That's the elevator.
Oh, okay.
Yeah.
Okay. Is there a reason why it's flickering so much? Like at some regions, it's changing a lot. So
So at some points, due to the course we have it trying to follow, it wants to vary the angle of the tech very quickly. And due to the parameters we have set, there are limits on how far it can deflect the elevator. And when it hits those limits, sometimes it causes it, to become off the predicted course or the course that it thought it would be on. And so it doesn't compensate correctly, but as you can see, it corrects itself after a short period of time.
Okay. So basically, those are because of the saturation function.
Yeah, correct.
Okay. Thank you.
So since you guys didn't get a chance to say it on your last slides, what would you guys do different if you guys had more time?
If we had more time, I think we'd definitely go into the ship dynamics and get those working alongside the autopilot. As I said, we did start on that, but we never got it to work together before this final presentation. So that would be one major goal, yeah.
And then I would also want to implement more predictive stuff so that we could, tell what time we're going to be landing at and stuff like that.
Okay, cool. Any other questions for Team 9? Again, repeating, this is Team 9. So
yeah. So you were talking about zones, correct? Zone 1, Zone 2, Zone 3. Is it just based on the distance between from the ship, and the need for that? Yeah, please, if you can describe.
Here, I'll switch back to the slide while I talk about it. So yeah, the zones are, we just want to have one zone where we're flying in a circle around, or here's the zones. So the zones are based on what side of the line we're obviously on. And the purpose of that was just to make sure that when we got our course heading we wanted, we were at a sufficient distance back.
And the alignment of that with respect to the direction of the ship, is it possible to understand that a little bit? The Zone 1.
Oh wait, like the location of Zone 1 and Zone 2?
Right.
Yeah, it's just given an arbitrary distance d back from the boat. So like I chose 150 because that's usually what worked best for me.
Okay.
There's no like finite reason for it though.
Sure. Yeah, looks pretty.
Yeah, this is
Yeah.
good stuff. I think you did at least I'm very much impressed by the math and thinking that you guys have put in.
Thank you.
Yeah, I would like the ship to move also, dynamics, but yeah, good stuff.
Yeah, sorry for the inconvenience that my internet crashing caused. Hopefully that didn't cause too much of an issue.
We're good. So this was Team 9. Let's move to Team 11 now. Team 11, you're up. And
Okay, can everyone hear me?
yes.
Okay. We're Team 11, and we were tasked with finding or landing a fixed-wing UAV on a moving ship.
So the goal of this project was to model a simulation of UAV landing on a carrier, just a moving ship. Our objectives were to adapt our animation, dynamics, and autopilot files from similar and previous assignments to work for this application. And we needed to lower the UAV altitude and velocity to eventually land on the ship. This has relevance to the DoD currently. From research, I found that the software for this has not been fully developed yet, and this could be useful in our future careers, especially if we work for like the Navy or something.
So for the contributions, we researched to learn what type of system is used to land a UAV on a moving ship. And then we created the animations in MATLAB for our UAV and our ship. And then we just altered our files from previous homework assignments and projects from this class.
So the research that we did, we found a few papers that kind of helped guide us through this project. Some of them provided more theory and some provided more like specific information and equations that we were able to use to model. And then we also used the homework autopilot assignment, use that to model basically the entire UAV. And then this has like the real world applications for the military and other necessary aircraft, water landings, and things like that.
So for the modeling, we actually modeled the UAV first by taking our autopilot code from the class and used that for most of the dynamics behind the UAV. And we were modeling the ship as steadily moving through the water, where we can orient the axis in which the ship is referenced in just in its forward direction so that it could be traveling exclusively along the north axis was our case. And the UAV was controlled by our autopilot file to land on the ship. And that was, we were giving the autopilot file a set of flight conditions to meet that would match up with the landing in terms of as the UAV was coming around. If it met the certain flight conditions, that meant that it was going in for a good landing. The assumptions that we made during this were that the waters were calm and that the boat was not rocking. This is not always true, but for our time constraints, we didn't want to get into the waters of waves and stuff like that. And there's an arresting gear system on the ship to decelerate the UAV. That's referring to either the cable or in some cases a net that would help catch the aircraft. And that would help slow it down a lot once it actually got onto the deck of the ship.
In terms of our autopilot that we use to land the UAV on the ship, this is a screenshot that I took that basically covers it. We give it a commanded airspeed, and then we set the heading of the ship and the UAV to 0 degrees, and we command the aircraft down to an altitude of 30 meters, which is the height of the deck of the ship above the surface of the water.
So for the simulation setup, this is just some of the initial parameters that we started with. Over on the left, we can see the ship dynamics. And as I mentioned before, it's pretty simple we oriented the axis about the ship so that it was only traveling in the north direction, which I believe would be Y if you were looking at a standard Cartesian. And up in the very top left, you can see the value 605 and below that 25. 605 is the initial starting position of the ship. We put it in front of the UAV so that the UAV actually had some room to come in and land. And that 25 is it's the speed in which the ship is traveling. So we left it at a constant velocity, and it's just going forward at that 25. I believe that's meters per second. And over on the right side, we see the UAV parameters, and this would be post whatever its mission was. Since we're concerned about the landing, we don't really have any care for what it did before. We just care about the parameters right when it initiates landing. So this is just what we estimated it to be. We assumed that the UAV was coming in from behind the ship, so it didn't have to make any major heading changes or pull any large turns.
So to the right are two screenshots that I took of the final positions of each of the vehicles. So at time t equals 30 seconds, you can see that they're both in the same position as each other, which would simulate the plane landing on the ship with our assumption of the arresting gear on the ship. And there are the gains and on all the different graphs over on the left that show how the plane changed with respect to the autopilot guiding it down to the ship.
So we were able to successfully model both the plane and the moving ship, but due to our limited knowledge of MATLAB, we struggled to combine them both into the same animation. We were messing around with it, and we kind of got one working, but it was really hard to see both the plane and the ship just due to our axes, and we could have improved the project by having more time and being able to improve on our skills in MATLAB and correcting our simulation to display both the ship and the UAV in the same model. So yeah, gaining a better understanding of MATLAB and how to combine the two models into the singular animation would have helped us more clearly show our final result, because we just decided to show in two separate animations that they both land at the same coordinates at the same amount of time. Additional dynamics effects on the ship, like the water currents, the waves, wind, could improve the model to get closer to the real world applications we were looking for.
That's it. Thank you for your attention. Any questions?
Questions? So did you have animation working in two separate windows, or was that?
Yeah,
we did.
They were two separate animations, yeah.
So was it working? Did you record one, or?
Oh yeah, I can just show you like the unedited video. So
while he pulls up that video, I do want to put it out there that we are a little disappointed that we couldn't get the whole animation together, but we did have a logistical hiccup because we had a team member drop out. So there was a lot of short-term schedule changes that happened really quick, a bit close to the deadline. So we were kind of scrambling to reorganize and redistribute the work a little bit.
So that was the plane, and then that's after 30 seconds, and then this for the time appears faster, so it seems like the boat is going really fast, but that's after the same amount of time, and they end up getting to the same position. So
you were not able to put two windows side by side together, two figures side by side.
Not in the same animation, no.
Okay. Questions, guys? Anybody? So did you have, like, was your boat moving?
Yeah, the boat and
Yeah.
the boat were both moving. And after 30 seconds of time, we were able to align the plane at 30 meters above the water, which is where our deck was located. I don't know if you guys want to pull up the like the results picture that showed that. But yeah, so we had the plane and the boat landing at the same coordinates at t equals 30 seconds. However, the plane was just located 30 meters above the water, which is where the height of the deck was. So both of the ship and the UAV were moving, and then at t equals 30 seconds, we just kind of simulated the landing on the ship at the same coordinates.
What was your success rate like only, was it out of 100 times? Was it always doing it different from starting from random positions, or?
No, we had a initial set of coordinates for each of the vehicles.
Okay. Any other questions from anybody?
I don't have any.
Okay. Sounds good. Thank you, Team 11. Let's move to Team 12. So 2 more presentations to go. We are moving across. So this is Team.
Yeah, this is Team 12.
Yeah.
Yeah, I did not miss anybody, right? Team 12.
I believe we're all here.
Okay, good.
Yeah, we're all here.
Thank you. All yours.
All right, we are Team 12. We are doing orbital refueling. It is Jackson, Charles, myself, and Tyler. This is what we're going for here, the Starship model. The orbital refueling where it flips around and kind of backs into itself and transfers propellant. And I'll hand it off to Tyler.
All right. So this is our table of contents, what we're going to go through today in these slides. Introduction, contributions, and the related work, along with problem statement modeling, all the control objectives, simulation setup, the results, discussion, and eventually conclusions. Next slide. So the introduction. So what we're doing here is doing orbital refueling, so the auto docking sequence of SpaceX Starship model. So when escaping, for example, you require a lot of fuel. So this becomes a constraint for the interplanetary travel. So one solution to this will be orbital refueling. So this will be prevalent to the future of space travel. So the idea is that once the rocket is in orbit, tanker come up behind it, connect to it, dock with it, and refuel the rocket, and continue to go off somewhere else.
Sorry about that. Uh-oh. Sorry about that.
All right, no worries.
Next slide.
And then, let me one more. And then to minimize human error, we're going to include a PID controller to create an autopilot with this docking sequence. Next slide. So contributions to this, we're going to show that the spacecraft can converge onto that spacer can converge into the target craft using XYZ coordinates. We're going to represent the rendezvous graphically and derive the equations, motions, and forces and moments to describe the rendezvous of the crafts, along with creating a PID controller for that. Next slide. So some related work to this. So the use of PID controllers in spacecraft is, and in docking is nothing new. SpaceX actually on their website has this cool little simulation that can be done for the Dragon capsule docking on the ISS. and looking at GitHub and related places, the PID controllers are used all over the internet. And with that, also references at the end, also included in that related work. Next slide. So the problem statement here, so we're to be given an initial starting location and velocity, and our goal is to get that chaser craft to rendezvous with the target craft, matching its orientation, and have minimal momentum at the point of contact. And below is that just representation of what we plan to do. And I'll pass it off to Charles.
So we decided to model our spacecraft with 6 degrees of freedom because in space it is unconstrained really by any means. So we modeled it off of the equations of motion we derived from small unmanned aircraft theory and practice in our class. And they're shown there. Next slide, please. Okay, and I'll give a brief overview of RCS thrusters, which is what we'll be using to make changes to our force vector and direction. So the layout is shown there in the top right. That's a general model of our spacecraft body. It's a lot more complex than a cube, of course, but each thruster will be equally spaced on each axis. We'll assume that the thrusters are located at precise locations that should any force occur, it would be around or through the same axis as the center of mass. So this would allow for very precise movements. We don't have to worry about tiny little moments created because everything is nice and balanced. So next slide. And so our forces, because we're in space, we're assuming there's no aerodynamic forces acting upon each spacecraft, and our frame of reference is going to be pretty close to the point of docking. So because they're so close, we're going to currently ignore orbital mechanics and say that our forces are simply due to propulsion. Next slide, please. And for our moments are very important because our spacecraft body is so complex. We're going to deduce that just through standard moment equation, where length is a measurement in the respective axis between the center of mass and the plane to which the thrusters rest on each face. Next slide, please. And for torques, I've got a little diagram there further showing the numbering of each of the thrusters. And so our torque equation, we're doing the same thing in terms of determining the radius with the length. However, here we're taking into account each of the thrusters that has an impact on torque in either axis. And both moment of torque follow the right-hand rule, so that determines which values are positive and which are negative. Next slide, please. And here is a summary of all of our equations, and I'll hand it off to the next slide.
So our control objectives here are to model the two bodies in Simulink, the chaser and the target. Apply the equations of motion that Charles went through to simulate the orbital conditions on the bodies, and then to implement the PID controller to autonomously dock them. The setup we used, the PID controller we used, we found on, or we did in MATLAB. It's a pretty crude system here. Pretty simple rendezvous waypoint sort of code that will be shown in more detail in a few more slides. In Simulink, we control these coordinates instead of just manually editing them, and they'll be determined by the distance between the spacecraft and the target, the chaser and the target. So that can be done autonomously. And then For the setup, this should look familiar because it's basically the UAV autopilot, just with instead of giving it a target height, velocity, and course angle, we're giving it X, Y, and Z. So it takes those as inputs, goes into the autopilot, and calculates forces and moments just like the homework, and outputs animation. So the parameters we're using were chosen based on previous assumptions. Like we said, we're not really taking orbital mechanics into account or like propellant transfer or anything like that. We're keeping it pretty simple. So then the randomly generated initial conditions are input in the Simulink file. So in terms of outputs, on the left here is the waypoint. The waypoint kind of model that we were using. This isn't exactly what we were shooting for because obviously spacecrafts don't maneuver like that in orbit. They don't. That's more like an airplane thrust, how it kind of moves. As well as on the right, that's a plot output from the UAV homework, but it's similar to what we would get if we were able to get it working. Besides the pitch, so as you can see, the height here, or well, it goes to a specified X, Y, and Z coordinate, and it should stay level and not pitch or yaw or anything to keep it lined up right. So our control objectives, we are modeling 2 bodies in Simulink, applying equations of motion, using a PID controller to do all that, to dock them autonomously. And we've succeeded in most. We got some models working, but applying the PID controller to the Simulink was very difficult. We couldn't really get it working correctly to where we could give it coordinates and it would autonomously move and find the right spot. We had the waypoint thing working correctly, but applying it to our model was a big challenge, and we couldn't really get that working correctly. And we'll hand it off to Jackson.
So besides that, our results show like a fairly promising attempt at simulating the real-world conclusions and aspects of a orbital docking, and we are pleased with our outcome of what we were able to achieve. Some of the limitations did come from the assumptions of like orbital mechanics being assumed nominal. We do believe our results were accurate, assuming the orbital mechanic influences on the forces were nominal. To develop a more realistic model, we'd like to increase the complexity by simulating many factors that includes such as starting from further in the flight path, even as far as liftoff from Earth or whatever planet, to then the actual docking procedure. A positive outcome of this, however, is that we would begin our initial conditions much further away, like I just said, and then we can simulate the orbital relative to the planet body itself, as in we could keep a tanker in a stationary orbit and then bring whatever spacecraft needs that refueling to it. You can go to the next slide. This model can be extended to include much more complexity. Obviously, things such as the planetary body itself can be added in, different hazards that can be included in that orbit, and different effects obviously will have much greater effect on our satellite and chaser and trailer. Another thing we would like to add further down the line is the actual mass transfer of the propellant and the mass consumed by the chaser vehicle, because obviously as these tankers and things are moving around, they're using their own propellant. So changing that would create more forces of motion and moments on each spacecraft.
Okay.
Those are our references.
Okay, thank you. Thank you, guys. So quick questions from Team 12.
So your vehicle had a total of, I think, 12 thrusters, correct?
Yes.
And how many of that thrusters were used in your simulation?
All of them were used. However, they were fired specifically in the respective faces. So we had no actual rotation of our body in this simulation.
Okay, there's no rotation.
We left our equations of motion open to accommodate that, though, in the future, once we start adding to the complexity of our simulation.
And is that the number of thrusters? Is that you know, that does it match the like a real vehicle?
I'm unsure specifically of the real vehicle. There could be more, but in ours we simplified it down to 2 per face in that orientation to and assuming that each one has the same max force output. But in real world conditions, I've seen many different configurations of those.
Okay. Okay, thank you.
You're welcome.
Other questions?
So did you guys actually get anything simulated, or actually something that we can see, or did you guys get stuck on the math?
We got a crude PID controller working that was outputting our flight path as well as velocity in each, or axial velocity, axial acceleration, and axial force over time. But we were unable to get that hooked up with Simulink to actually get an animation of that, although we can show the plots if you like.
No, that's okay. Thank you, though.
All right, you're welcome.
Awesome. Any other questions? Great. Let's move on to the final presentation of the semester, Team 13. Okay, all yours. Time starts now.
Good morning, everyone. This is Team 13. I'm Emily, and the rest of the team members are listed on the slide here. And we'll be talking about our final project, modeling and simulating an autonomous sailboat. These are all of the things that we will be going over today. Electrical power is a limited resource for autonomous sailboat missions because there's no necessary passengers, so electrical power is that limiting factor. So modeling and simulations of sailboats can provide an efficient and low-cost media for experimentation, especially when it comes to developing power-saving strategies and developing controls. And the point of developing controls would be to decrease power necessary for those controls to hopefully extend duration of missions. Some clear objectives that we set out to accomplish were we were to model a sailboat that would output reliable state estimations. As reference to an actual sailboat, we were to develop a controller for autonomous dynamics so that no human input would be necessary. And we were to simulate an autonomous sailboat in MATLAB using those developed models and controls so that this simulation could be used for experiments in the future. The impact of developing an autonomous sailboat on the field is that it can be used for long surveillance missions, seafloor mapping, and other marine research. And it can also be used for transporting goods and passengers with carbon dioxide neutral emissions.
Right, so these are the contributions to the collective work on autonomous sailboats. We model a sailboat by considering the defined state space consisting of the X and Y position, heading, sailboat speed, and rotational speed. There's also true and apparent wind and aerodynamic forces. We develop a controller for autonomous motion by combining the use of PID and fuzzy logic. which makes the sailboat capable of traveling at an inputted heading and also between specified waypoints. And we simulated the sailboat in MATLAB using computer-aided design for a sophisticated simulation. And this also gave us, this also outputted plots that were easy for analysis. And there's also potential use for power strategy experiments. Slide. So these are the related works to our project and where our work fits. This project was based on the work of John Mellon. In his work, Mellon explores the use of PID and sign controllers for the same problem statement. And by considering Mellon's work in applying the PID controller, we developed a hybrid controller including fuzzy logic for the same autonomous sailboat problem. And the fuzzy logic controller was based on earlier work by Vijay Kumar Suresh Kumar. Suresh Kumar used a FLC or a fuzzy logic controller for control of a quadcopter, and the system set out in his paper was replicated and changed to fit for the commanded value to the rudder of our sailboat. Slide.
So when creating our model in Simulink, we had to make a few assumptions to work within the scope and time of this project. So we confine the motion to the X and Y plane. This basically meant we assumed that there are no wave or current influences creating vertical motion on our sailboat. We also neglected the Coriolis effect and centripetal forces, as the scope of our travel wouldn't include that. And the mainsail and foresail were combined to act as one effective sail, so we wanted to account for one sail angle and force. We modeled the state space as the positions X and Y, our heading angle theta, our sail spoke speed v, and our rotational speed omega. And then our control signals were our rudder and sail angle, as you can see in figures 4 and 5. So, slide, please. So then our equations of motion showing all of our dot states, all of our changing states. In that X and Y depended on the drift due to change of position, also wind speed and our direction. And then our theta, which is our heading angle, just depends on the change in heading for multiple inputs. Our change in our sailboat velocity actually depends on the sailboat propulsion, just from the sail, our braking rudder force, and also the body friction defined in our model. And then our change in our gamma angle depends on the difference in moments. And the model also depends on some of our model parameters, such as our body friction, our rudder lift, and some of the other defined parameters of our specific sailboat. Slide, please.
The control objectives problem, we used a combination of PID control and fuzzy logic so that the sailboat can go from its current waypoint to an inputted waypoint list of waypoints. And the flow of this is as follows. The destination waypoint is inputted, the required heading is calculated, and the control loop maintains the required state space until the waypoint is reached. You can see the feedback loop diagram typically seen for fuzzy logic controllers, where you give it a input, say a desired heading of 5 degrees. You would normalize that to a range of -1 to 1. You fuzzify, which I would get into, but that would take me quite a while. And then you use the fuzzy rule base, which I'll explain on the next slide, to determine the input to output relationship. You go back, please. And then you would defuzzify that result, which would get you a commanded PWM to the motor, which you would then input to your plant, which gets you your output and states. Next slide, please. So for the simulation setup, this was kind of the baseline we started with. You have rudder angle, sail angle, wind magnitude, wind heading as all your inputs. You'll see later that the rudder angle gets replaced with all of our controls, and the sail angle gets replaced simple expression for the sail angle given by John Mellon's previous work. And next one. So the simulation parameters Sebastian talked about earlier are seen on the left. Stuff like mass of the boat, moment of inertia, etc. And onto the desired course calculation. The UAV toolbox actually has a nice setup for this already, so we went ahead and used that because I'd used it before. You input the states, aka the pose as they call it, your set of waypoints, and a look-ahead distance, and it outputs a desired course. You can see that kind of in the bottom diagram there. If you have a longer look-ahead distance, that phi, or the commanded heading, is going to be smaller, so you have less aggressive of a turn trying to get back to that normal line. Next slide. So onto the heading with fuzzy logic. On the left, you'll see it's set up so it accepts error and previous error, and then inside of the fuzzy system, it'll compute the error dot, which then get sent into the rule base. So for example, if your error is negative low and your error dot is 0, then you get a negative small PWM value commanded to the motor, which adjusts the sailboat back to your design heading. And if you put this in a nice 3D, you can see the input to output space, and notably it's symmetric, so same inputs but opposite give you the same output but opposite. Next. So on to some results. This was a simulation done where the boat would travel straight north, then a little bit northwest, then northeast. It has a look-ahead distance of 5. That's what we tested and found out to be the best. And the wind is 80. That'd be meters per second. It works under smaller winds because 80 meters per second is a lot, obviously. But for the speed of simulation, we ramp that up. And you can see the PID controller response on the left. This is blue is your desired heading, and yellow is your actual heading. And the PID tends to be quite sluggish and doesn't always converge. It does okay, but as you can see compared to the fuzzy controller, it does much better with the fuzzy controller. It has much quicker rise times, settling time, and very little overshoot. The PID controller, by the way, was tuned somewhat roughly. Better tuning could be used, which would get somewhat better results, but from a quick tune, this was about the best we were getting.
Okay, so this is just a little video. Feel free to skip through it a little bit just to get quickly through it. It's just showing the boat following a few waypoints. So you can just skip to a few different points. You can see the boat kind of turns and go into a point. You see right there, there's an XY chart on the scope right there. You'll see that the boat begins to kind of, you see that the values shift as the boat turns and goes to its next waypoint. You can feel free to just go to the next slide if you want. But yeah, just a little demonstration of the waypoint following. So some issues with kind of sailboats is that if you want that a very large commanded angle, as you can see that figure to the left, it can take a really long time for the boat to reach that commanded angle because the rudder can only turn so far. And then also, if the winds are unfavorable, if they're outside of a sort of 30-degree angle within the heading of the boat, then the desired heading of the boat, then it has a difficulty going to its desired location. As you can see in that chart to the right, right there, the boat turns into the wind and tries to make use of it, but it stalls out and kind of just drifts because it can't go anywhere because the wind is not blowing in favorable directions. So slide. Finally, so for our conclusions, we're very happy with our performance of the fuzzy logic controller. We felt that worked very well compared to the PID controller. However, there are some situations where it still has difficulty, as it is a sailboat. It depends on the wind a lot. So for the future, we perhaps are considering adding some sort of algorithms that the boat can kind of strafe and work with those non-ideal winds. Additionally, factoring in more randomness into the simulation with wind strength and heading kind of having noise. And then on top of that, some waves and some of those assumptions that we made, kind of getting rid of those and having a more holistic simulation. And then finally, also this current model could be implemented into a real autonomous sailboat in the future using MATLAB's code generator toolbox. So, slide. Those are references, John Mellon and of course George Kumar. And thank you. If you have any questions, ask them now.
I have a question.
First of all, I just want to say that's really cool that you guys were able to implement fuzzy AI into your algorithm. I was wondering, how do you get fuzzy into MATLAB?
So I can cover that. There is a fuzzy logic toolbox in MATLAB. In the past, I've used that. It's not capable of being used C++, the code generation. So I went ahead and had to make my own in the past. So I just applied that there. You have to go through all of the math and whatnot, which I won't get into. But basically, I had to make it from scratch for this and previous projects.
Also, why a sailboat? Obviously, sailboats are getting less common, and it seems like there's a lot of variables that are hard to control for. So what benefits does a sailboat have over like a conventional like propulsion method?
We were talking about earlier with some of those kind of on the early slides, talking about kind of these low power solutions to kind of getting stuff out in the ocean, some kind of kind of like, I guess, like drones, but except on the water. But using a low amount of power, being carbon neutral, those sorts of solutions could be why a sailboat might be beneficial to use.
That's super awesome. Well done.
Yeah. So I had a question. So obviously, it's one of the limitations of the sailboat is the directions in which it can move are based on the wind direction. Correct? For example, you won't be able to make it move like perpendicular to the wind direction. So have you done any tests on what's the range of movements it can achieve? What is the range in which you can give those direction commands?
Yeah, so from my experience, maybe William can comment on this as well. That 30-degree range we talked about, basically at any wind direction, it can get to the correct heading, but with how it's set up right now, if it's sailing straight into the wind, it's got the correct heading, but the wind pushes it backwards. Anything outside of that 30-degree range, it can't really track X, Y, it just tracks heading.
I see. Okay. Thank you.
So have you guys thought of a hybrid? I think a hybrid model would have been Prashant, go ahead.
No, I was just going to add that if you have multiple sails, you can basically make sure that it heads wherever you want it to head with a little bit more control. And plus, as Dr. Sharma is saying, maybe hybrid might be another one.
And then an optimal switching between propeller and sail would have been nice.
Yeah, that's it.
But this is very complex, so good job.
Yeah, good stuff, guys. Other questions, Matt and Anushna?
No, I don't have any questions right now. I mean, the fuzzy logic was going to be one of my questions, but it was asked by one of the other previous students. So, no, good job. I mean, it's definitely a complex thing, but I think it's stretching above the bounds of normalcy. So I think it's a good attempt at that. Thank you.
Awesome, Anushna.
No questions from my side.
Yeah, great. So I would have to talk in details how fuzzy logic performed better than PID control later, maybe. But yeah.
I'd love to get into that if I could email you or vice versa. I'd be down.
Awesome. So I think that kind of concludes. So judges, please fill out the forms you have, and I really want to thank you. Everyone for coming out. It was a great semester. I really enjoyed, as I said, like projects you guys have done and the amount of material that we have covered. For example, the aerial refueling problem or the sailboat or orbital rendezvous. These guys have to read papers which were, when you write papers, it takes 2 or 3 years at graduate PhD level, and these guys have read them. So that's one capability these guys got, and the class that as a class they can read a paper and implement it. So I'm very much impressed. And any comments? I think the final comments from judges. What do you, any overall?
Yes.
Yes, please
No,
go
go
ahead.
ahead.
No, I think they were all pretty impressive. Really amazing job by all the teams. Yeah.
No, I was gonna say I think it was a very good job by all of you guys. I think you guys all experienced different real life scenarios. Losing a participant. Trying to over put your expectations on your projects. And then finding out time gets on. Is your worst enemy. But everything that you guys have worked, is basically what we're doing in the government, systems of systems, interfacing, and that's what you guys are doing. So you guys are learning exactly what we are pretty much learning as well as we're working on everyday real projects. So good on everybody on everything you guys have done. Good job. I know it's you guys are probably excited to get this done. But what you guys did in 2 and 3 weeks is definitely an applause to you guys. So keep it up. And always let me know if there's anything I can do to help. The Navy's always looking for good engineers and mathematicians and scientists. So if you guys are interested in co-ops, let me know. Those are always definitely something we're always looking for. I think the window's kind of already passed for this summer, but there's always opportunities. So always willing to help you guys with resumes. We do modeling for different stuff. So if you guys have questions, I'm always willing to help on some of that stuff. So good on you guys. Congratulations.
Yeah, I just want to echo the same what Matt and Krishna said. Very good job. And especially in the last year, everything has been difficult, and I applaud your resilience throughout, and have a great summer.
Anushna?
Excellent presentation from everyone. I really liked all the simulations you all did. It was really good. And it was great to see so many different ideations and executions of these projects. And like everyone else said before me, last year was difficult in so many senses, but they're still getting to do this in an online class and still getting these projects done. This was great job. So kudos, guys.
Yeah, I would say like now the simulation level or animation level you guys have, I cannot do these simulations. That's the comment I want to give. Like you guys have reached beyond my capabilities of simulation and animation. So good job, guys. Anybody wants to share anything from the class team, students?
Yeah, I just wanted to quickly, thank the judges for sure. Thank you guys for taking all the time out of your day.
Thank you. Anybody else?
Raj, are you going to share the recording of this?
Yeah, share. I will definitely. So I will be putting it on YouTube, LinkedIn, and I will also share. Once I get the results, I will also announce the winners of the competition, and And guys, don't forget, we will be there in campus, maybe hopefully in the fall, and come by, swing by my office, we can grab, Subway or pizza or something, whatever. So yeah, drop by, swing by, and good luck with everything for your co-ops. And I will get back to you with results. It will be a hard job, I'm sure. There are all good presentations.
So Raj, are all the presentations posted on that site that you sent out? Just so we can go back to them if we need to.
I think I'm missing. I did put everything except Team 9 and Team 12. Presentations are not. So if Team 9 and 12, you guys can send me your presentations, I can upload on the folder so judges can see them.
Perfect.
And Matt, I'll also upload that on the our whole project's website for long-term archival there, so it will also be available there.
Okay, perfect. Yeah, just so I can go back to them if I need to.
Sure. Will do.
Dr. Sharma.
Also, shout out to Dr. Sharma. It was a really fun semester. Thank you so much.
Welcome. Thank
Dr.
you.
Sharma, about the presentations, this is David from Team 2. I sent you an email with our
yours is there.
Updated slides.
Okay, updated. Yeah, I will put
it because we made some changes between when I emailed you last and what we presented today. So I sent you the slides that we used today.
Sure, I will update that.
All right. Thank you.
Thank you, everyone. You have a great rest of the day and summer, and enjoy. Thank you.
Thank you.
Bye.
Have a great
Thank
day.
you.
Thank you.
Thanks, everyone.
Thank you all.
Thank
you. Thanks for a great semester.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.